people using, living in smart cities. However, what is missing from this picture is how the human will react, the traveler will react to this connected and automated vehicle technologies, and in particular, what would be the tendency, how we can alter the tendency to travel. There have been several studies indicating that although we can have benefits, obvious benefits in using connectivity and automation, these studies have also indicated that there may be some, rebound effects. As you can see in this graph, you all recognize that platooning, eco-driving, and other technologies can definitely have some impact, positive impact on reducing the energy. But at the same time, there are some rebound effects. For example, if travel cost reduction is, if we have travel cost reduction due to the connectivity and automation, then this might also, increase energy consumption, and this can be visualized given the fact that if we reduce the travel cost, then people might have the tendency to travel more often or use their car more often, which in turn will increase vehicles miles travel, and this will have a rebound effect. So what we try to do with Ioannis in this work is to take a socio-technical system approach and consider the decision-making of the traveler. So we want to make the put the traveler into the loop and try to understand how all these technologies can affect travelers' behavior and see how we can account for this. So what I plan to do within the next 20 minutes or so is to go through the modeling framework and then come up with a centralized problem that can capture how we can eventually control travel demand. And we do that by designing specific incentives that we can provide to the travelers. And then I will summarize the talk with some main results and take-home messages. So imagine that we have, we have a smart city. We have a city that can accommodate connected automated vehicles technologies. And we have a social planner, which can be a central computer, a central authority in the city that can accommodate all the travel requests. So imagine that all the travelers can put, identify the request every morning through an app, given the desired origin destinations, and then the social planner, which is a central computer, will take all this travel demand along with the preferences and allocate the mobility services. The mobility services can be any available mobility system in the city. For example, we can have the privately owned CAVs or privately owned cars. We can have bikes, subways, public transportation overall. So all of these are considered mobility systems, and the social planner, what the social planner needs to do is to allocate the desired origin destination to these available mobility systems in a way that we can have a socially optimal, efficient mobility system. By saying socially optimal mobility system, we mean a mobility system which is energy efficient, but at the same time doesn't, create rebound effects. So essentially, what we want to do is to, allocate the origin destinations through some messages accommodated by the app to the, available mobility systems in the city. And as I will explain later on, the way that we can do this by designing a mechanism, by imposing a game among the travelers, so that at the equilibrium of this game, we have a social optimal mobility system. And the way that we can do this, it will become obvious in a little while. So in our approach, we consider that we have n travelers. This is the set of travelers I. And then we partition this traveler given the origin destination. So for example, all the travelers whose origin is within a neighborhood, right? A big neighborhood, a big area. And also the destination is also close to another neighborhood. We cluster these travelers to some subset IK. And in order, we do that in a sense to accommodate a little bit, any computational applications for considering all the single origin destinations. And then we also consider that we have M mobility services in our city. And then we define the travel service assignment, which is the parameter AIJ, which is for every traveler I. If for every traveler I we assign a mobility service J, then the IAJ is equal to 1, otherwise it's equal to 0. And we also consider that the vector AK that corresponds to a subclass IK of the travelers, considers all the associated travel service assignments. Then in the next step, we define the personal travel requirements for each traveler I. These personal travel requirements considered is a tuple that includes the following 3 pieces of information. First is the theta I, which is the preferred travel time of a given traveler. So if the traveler I, let's say, has a specific origin destination, the traveler might have a specific preferred travel time for his origin destination given her past experience. The second piece of information is the maximum preferred number of co-travelers. So for example, if the traveler I is going to use, let's say, a share mobility, Uber or Lyft, then the traveler might indicate that she doesn't prefer to have any co-travelers in the car, or she might prefer to have only one. We need to capture this in our modeling framework. And finally, the last piece of information in the personal travel requirements pi I is the delta IJ, which is the monetary value I of the traveler I who is willing to pay or receive using the mobility service J. So for example, a traveler I might say, I might be willing to pay X amount of dollars if I can use a CAV or Uber or Lyft and so forth and so on. Next, we define the so-called mobility inconvenience metric, which captures the inconvenience of the traveler given a selection from the social planner. So for example, if the social planner assigns the traveler to, or suggests rather, the traveler to a given mobility service, then the traveler might experience a specific theta I tilde travel time, right? And at the same time, given this suggestion, the traveler might experience a psi I number of travelers within this, mobility service. So all these parameters capture the inconvenience metric of the travelers, which is a function of his private information, which is the travel requirements pi I, the theta I tilde, which is the travel time experienced with this mobility service J, and also the true number of co-travelers of a given mobility service. And as you can imagine, the higher the travel time, the experienced travel time, theta I delta, and the higher the number of co-travelers psi I for each particular mobility service, then the higher the inconvenience metric. So you can see how we have modeled the inconvenience metric to capture the impact of the experienced travel time and also the number of co-travelers within the mobility service I. Next, we also define the metric of traveler satisfaction, which is essentially the difference between the maximum value that the traveler, VI bar, the maximum value that the traveler I can get if there is no travel delays within by using the mobility service J, minus the inconvenience metric. So VI bar is the maximum value that the traveler can experience if the traveler uses mobility service J and everything comes to his or her preference. And of course, given the mobility satisfaction, we can define the utility of the traveler I, which is the difference between the mobility satisfaction minus some mobility payment. And eventually this mobility payment is our control input. This is how, how we will end up, using in order for us to convince a traveler to select a particular mobility service J. So this is the control input that we eventually have to design, how the whole problem will end up being how to can design the appropriate mobility payments that can convince the travelers to follow up the suggestion of the social planner. And before we formulate the problem, we need, of course, to define the cost, associated cost of each mobility service J, which considers both the overhead related to operating labor, fuel, energy consumption, and so forth and so on, but also the societal cost, which is the impact of each traveler using the mobility service to the footprint of transportation or environmental cost. So we sort of assume that we have in place a mechanism, a way that can sort of, compute the distribution of the travelers to each mobility service related to the cost. After defining the cost, we are able to formulate a problem which is minimizing the inconvenience metric of all travelers plus the cost of all mobility service. Subject to the following two set of constraints, we need to have assigned only one mobility service to each traveler. And of course, we need to make sure that when we assign all the mobility service, all the mobility assignments, then we don't exceed the maximum capacity of each mobility service. So for example, if a bus has a maximum number of 20 travelers, we cannot really assign 30 travelers to the bus, from this problem. Now, this is a typical integer programming model, and we could use, in other circumstances, typical standard algorithms to provide either to yield either the global optimal solution or, in the worst case scenario, approximate solutions. However, as you can imagine, pi I is unknown for us. So the social planner is dealing with an optimization problem with incomplete information, because pi I is the private information of each traveler, and the social planner doesn't really know about this private information. So essentially, the social planner, the central computer, cannot really solve this problem. And this comes to the solution approach that we have, Ioannis and I have taken to consider this problem. So instead of solving this problem in a centralized way, what we plan to do is to impose a game by designing a mechanism among the travelers. At the equilibrium of this game, we have the desired outcome, which is a social optimal mobility service. Now, just to give you a little bit of insight on this approach, if we assume for a moment that if we could ask all the travelers to give us their private information and they were truthful, then we could just, simply take the, theta, the agent's preferences, and design the social choice function that can give us the social allocation, the optimal. But as you can imagine, the travelers might be greedy, might be strategic, might be lying, right? So we can't really count, on the fact that the social planners would be truthful. And in order to avoid this, we will, implement or develop a truth elicitation problem, in which we will allow some sort of messaging between the travelers and the social planners, and we, impose a game. We will design an outcome function, and these travelers will see, given this outcome function, what's the outcome of the messages, and at the end, we hope that the equilibrium of this game will, make them be truthful and reveal the truth preferences. So that's the outline of the whole idea. In order for us now to solve this problem, it seems that I have some issues changing slide. Okay, here we are. Eventually, this is another summary of what I just said. We have the travelers. The travelers communicate through the app and through messages with a social planner, and the social planner now needs to design the tolls, fares, and fees, essentially the mobility payments that can convince the social planner to, first of all, participate in the game, and at the end, accept the suggestions imposed by the social outcome. If all of the travelers accept these suggestions from the social planner, then we can assure, as I will show you in a while, that we have ended up with a social optimal mobility system, an energy efficient mobility system without rebound effects. Now, since we want to design these mobility payments, it's more convenient for us, instead of dealing with a minimization problem, to deal with a maximization problem. So we can convert problem one, which was minimizing the inconvenience metric, the mobility inconvenience metric plus the cost, and with substituting this with maximizing the difference between the traveler satisfaction minus the cost. We can easily see that these are two equivalent problems, the solution of which are the same. However, there's one more problem with this formulation. What if the travelers are strategic? What if the travelers just simply reject any recommendation from the social planner, any solution of the problem 2? So in order to capture this type of travelers, we need again to add one more constraint into our problem 2, which is essentially the constraint 17, the equation 17 that we can find, which capture the fact that we might have some travelers which simply reject any recommendations from the social planner. So these travelers essentially will turn down any recommendation, and they will do whatever they want to do. By adding this constraint, we capture this behavior. So essentially, we end up dealing with the problem 3. And what we want to do is again to design the incentives, the mobility payments for each traveler I, so that eventually accept the suggestion for the social planner. It turns out that the appropriate mobility payments is the one which is the difference between the maximum welfare if the traveler I does not participate, minus the maximum welfare of all other travelers except I. So by putting this specific format of the payments, we will be able to have the following 3 major results in our problem formulation. The first major results that we can show is that all travelers will be truthful. Given these payments, we can prove, we prove mathematically that eventually we end up with a nice equilibrium, and all the rational payments is for the benefits to be truthful. If they deviate, if they are not truthful, it's not to the benefits to do so. The second outcome of this particular design of mobility payment is that all the travelers will voluntarily participate in this game. So nobody will, it's not to the benefits of any traveler to turn down any suggestion and say, yeah, I'm not going to participate in this game. And the final outcome, given these designs of the mobility payments, is that if we play this game for all the travelers, at the end we'll generate some revenue. And this revenue can be used to maintain the infrastructure of our smart city. So eventually this is a nice property of the mechanism in the sense that, after all, we generate some revenue and nobody pays anything about this. So we have a revenue generation that can be used to maintain and update in the future the infrastructure of the smart city. Now, there are some limitations of this proposed approach, and I guess you have already identified these limitations in the fact that this is a static game. So all the travelers will make this selection, the social planner will make the allocation, and that's it. We can't really change any of that. If any of the travelers change his desired origin destination, then we need to solve, the social planner needs to solve all these problems, all these, the problem 3, all at the beginning. Which is a major benefit. So we need to sort of to make it realistic and have some implications into reality. We need to make sure that we will be able to adjust in real time any potential modifications of the travelers. So this is a particular direction for future research, but before I get to the future work, let me summarize, the outcome of this effort, which is to design an emerging mobility system with 3 key properties. The first property is that all the travelers will be truthfully report their personal travel requirements. There will be the second one is that they will voluntarily be willing to participate in this mobility system. And the final outcome and the property is that this mobility system will eventually generate some revenue that we can use for maintaining the infrastructure of the smart city. There's still a couple of open questions that we're trying to address, and mainly is the impact of the connected automated vehicles on the transportation and what are the implications of that. We still need to understand a little bit more the traveler behavior, you saw several definitions of the mobility, inconvenience, metric, and traveler satisfaction. That's our mathematical oriented metrics. We need to make sure that we adjust these metrics through some traveler behavior, and we collaborate currently with several colleagues at the University of Delaware from the psychology department and brain science, and they're trying to bring this component into our framework. And of course, we need to make sure that we can adjust in real time any changes of the traveler's request. So we need to sort of move from the static setting to a more real-time dynamic setting, which is also part of ongoing work with Ioannis. So I think with this, I would like to thank you for your attention. I'd be happy to take any questions.
Thank you so much for the awesome talk. It's a very attractive framework for the smart cities. I do have one question. So what will be the biggest challenge during the transition from our current traditional mobility system to the smart mobility system that you proposed? How do we address them?
Well, the biggest challenge is, of course, the social aspect. How we can capture the behavior of the traveler, and make sure that we provide the incentives and also the suggestions that the travelers will eventually accept. There's going to be a learning curve. How travelers will adapt and use the advanced technologies in mobility, and in particular connectivity and automation. What will be the impact, the rebound effects, and how we can capture this. Although this framework, at least in theory, provides some answers, it's far from being close to a reality. And as I mentioned, there are several components that we need to incorporate, and most importantly, the human factor. We need to understand better how humans, and in particular travelers, make decisions, and what are the implications, and how we can, unless we understand this, then we can really capture the rebound, the potential rebound effects of, emerging mobility systems.
Got it. Thank you for explanation. Yeah. Any other questions from our audience? Feel free to send your questions through the chat box, or you can also unmute yourself to ask questions. Okay, cool. So with that, we can move on to our second talk from Professor Peng Huei. And let me introduce Dr. Peng Huei. Dr. Peng Huei is a Roger L. McCarthy Professor at the Department of Mechanical Engineering at the University of Michigan. He currently serves as the Director of MCD, which studies the connected and autonomous vehicle technologies and promotes their development. He is also the SAE Fellow and ASME Fellow. It's a pleasure to have you here. Really looking forward to your talk.
Okay, thank you, Yan and Andreas, for organizing this tutorial workshop. Can you see my share screen?
Yes.
Okay, great. Yeah, so I'm going to talk about automated driving in mixed traffic. In particular, we want to make sure that the automated driving systems can deal with human drivers. Much of the work is done with my research scientist, Dr. Xiaobing Xu. The key concept is that we know that the level 1, level 2 ADAS, Advanced Driver Assistance Systems, and ADS, Advanced Driving Systems, which is level 3 to level 5 SAE vehicles, need to share the roads with other road users. And we all know that being safe, of course, is not easy, but being safe alone is not enough. Just look at these two videos. The one on the left, you see that the Waymo vehicle hesitating at the unprotected left turn. Without a straight driving vehicle, maybe there is something happening at the pedestrian crosswalk. We don't know that because of the field of view. On the right-hand side, you can see a Waymo vehicle, which is trying to make a lane change to the left. And judging from the shadow on the ground, you can see that it's probably true that there is a gap in front of this big truck, and a human driver probably would accelerate and take the gap in front rather than just keeping waiting forever for the gap behind. So these are not safety concerns, but we know that these are not acceptable either. And we know that a robot sensing perception problem is receiving a lot of attentions already. Therefore, I'm not going to talk about the perception AI at all whatsoever. Instead, we'll be focusing on the prediction, planning, and control of problems for the autonomous vehicles. There are really four issues. The first two are much more addressed, more mature, but there are still problems to be solved in terms of motion control and also motion planning. The second two topics, predicting the behavior of human drivers as well as design AV for better roadmanship, which I will define later. But those two are more emerging, and I will spend more time talking about our work in the first two, even though we are also beginning to work on the emerging problems for the second two topics. So there are plenty of examples demonstrating that even people today are not necessarily mastering the motion control problem very well. While we don't have proof that this kind of problem is due to a particular issue, we do have observed this kind of silent behavior on our vehicles before. And our problem, again, I'm not speculating that's their problem too, is related to vehicle dynamics, in particular lag and delay. It is very common that we, the vehicle dynamics control guy, start to build something as physically inspired as possible, and this single track lateral yaw model is commonly used, and people use Newton-Euler equations to write down the governing equations, then into the state space form, but this is not sufficient. In fact, many of the control guys, especially the robust control guys and design correct by design kind of guys, think that you can just write down the governing equation and whatever you control will become your control input directly. But that's not true. In fact, this is an example for the MCT test vehicle. From the control algorithm all the way to the steering, there are many cases, subsystems in between. We do have an MCT safeguard system, making sure that the vehicle doesn't exceed a certain hardware bound or comfort bound and so forth. And then there are by-wire control, ROS drivers, some USB CAN interface, and then the data speed steering module, and then CAN network, and all of these subsystems in between really was generating two things. One, we call that delay. In other words, when you send out the command, the receive command, even before the actuator start to respond, has a very significant delay. The second, we would call that lag. In this case, we're using first order lag to approximate what happened because of the tire patch has some friction and your actuator has some current. It wouldn't go to the desired value instantaneously. And here we assume that there will be a first order lag that's happening even after your delayed receive command. Overall, for example, the test vehicle we have at the University of Michigan is that we would have 200 milliseconds of pure time delay and another 200 milliseconds of first order lag. So you can do various experiments to figure out the delay and lag your system has, but 400 milliseconds is just too large to ignore. If you don't address this, your motion control wouldn't be very nice. And how do we address that problem? Obviously, it really depends on your preference. I know many of you are very familiar with the model predictive control. this kind of formulation can take a lot of computation to solve. We actually were using the preview control algorithm, which is different from MPC, even though they have a lot of close correlation between them. We choose not to do MPC because of the computation load. In fact, we want to address two problems in one shot. One is to deal with the delay and lag. The second is something very, very related to the lateral control. We all know that the future road curvature is a previewable disturbance, and we can handle the future curvature information very nicely together with the preview control algorithm. And it's very nice to know that these two problems, lag and delay and preview of future curvature, can be dealt with together in a very uniform way by the preview control theory. Obviously, for this tutorial session, I wouldn't have time to talk about the detail, but obviously we have published the results in papers, and we can all understand that this is a framework that can be used to deal with the preview, the lag and delay, and also future curvatures together. Obviously, we have done some experiments, so if you handle everything well, then the steering will be very nice and smooth. You barely see much motion at the steering wheel, and the vehicle can track the future curvature very nicely. But in the meantime, if you look at the lower right corner, that is a slalom behavior that is very similar to the one that's demonstrated by the Siemens video I showed very early in this talk. So it's a very similar behavior. If you don't deal with lag and delay, or the value are very wrong, then it's very easy to have instability issue. All right, so that's the motion control problem, one of the very important problem we need to deal with at the very low level, at the motion control level. But let me talk about the motion planning, which I believe is a much harder, complex problem. But in the meantime, we think that we found a good way to solve that problem too. So in many cases, if you look at the papers in the literature, many cases people say, I'm solving this problem of, say, ramp merging, or roundabout entering, or right turn, left turn, or pedestrian, or door opening, or whatever problem. The situation is that we certainly are very happy to see very rigorous solution for any of this one scenario. But in the meantime, we want to design a scalable algorithm. There's no way we sit down and say, let me solve one scenario at a time. It will be much better if there is a motion planning algorithm that can handle both typical and atypical scenarios. In other words, it would be nice if we have an algorithm that can be scaled up to real-world driving without worrying about any one particular scenario. So motion planning stack design, so we definitely want to put in something into the test vehicle to emulate what Waymo, GM, Ford, and other people put into their vehicles. And obviously, when we are trying to imagine the problem of how to put in a automated vehicle driving stack into our test vehicle, we understand that the very high level problem, the routing, for example, shortest distance or fastest time or eco driving, eco routing problem need to be solved at the very high level. In the meantime, in the middle layer, we need to plan for desirable behavior and generating future trajectories. And that's really the problems we're solving, we're proposing, discussing below. And at very low level, of course, the motion control problem, like what I just talked about for preview control. So I'm going to address the middle layer, the problem of the trajectory generation. So the routing problem we solved was very simple. A-star entity was based on the A-star algorithm. And literally, you can click anywhere in the MCT and say, I'm here and I want to go there. You click and you can generate this A-star. So in this case, for this distance, very, very easily. That's not the hard problem. It's well understood, well solved. But in the meantime, of course, you need to smooth out your trajectory and make sure that you don't make some abrupt changes or turning that is not human-like. So there are a little bit of detail there, but nothing complicated to report. So let me talk about the middle layer problem, the behavior planar and trajectory generation. And typically we look ahead by 6 seconds, and basically we say, how do you generate the future trajectory for the future 6 seconds? That's really the problem we want to solve. And thinking about, again, we are imagining the need of making our algorithm scalable. Therefore, we divide up all the future scenarios into 3 types. Obviously, this may not be complete whatsoever, but at this moment, this 3 was used, and we are able to address almost every driving behavior happening inside MCT. How many different models or models of behavior planar do we need? Do we need many, like 20? No, actually, we found that we are able to capture most of the scenario in just 3 models. So the first model we have is you are making a multiple choice problem. So for example, in ramp entering, or in this case, if you are exiting from highway, sometimes you are also deciding, you're in front or behind a particular vehicle and so forth, or making a lane change. Do you want to change into gap 1, gap 2, or gap 3? So literally you are making this multiple choice problem of I could look at gap 1, gap 2, gap 3 and decide which one is better. And obviously there are some calculation you need to do, and you say that's feasible, not feasible, and which one is better. At the end, for example, if you say gap 1 is what I want to take, then your future trajectory will be very different. So this is one problem, and that's a multiple decision problem. The second, this is a feature showing, again, when you are merging into the highway, a lot of time, the most important first question to ask is, which gap do I take? Now, the second type of scenario model is much simpler. When you are heavily constrained by a lead vehicle, for example, and your primary constraint is the lead vehicle, and therefore you're basically saying, let me keep a safe time headway behind. This is a very relatively easy scenario, but this is a lot of the time we drive in this particular situation. So this is the second model. You want to project the future trajectory of the lead vehicle and try to follow it. And imagine where that vehicle will be and then plan your trajectory accordingly. The third kind of problem is actually, we call that a yielding model. Obviously, when we are coming to a stop sign or traffic signal, it's not a yielding model. In the meantime, you can see a lot of yielding decision. For example, entering a roundabout. If there is a car upstream on your left-hand side that's already inside the roundabout, you need to yield to it. So sometimes you have to come to a full stop. Sometimes you don't. And then the second example is at the intersection, unprotected left turn or right turn and so forth. So the question of, do you come to a full stop or not, that is a decision you need to make. Anyway, so this is a yielding model, cover quite a few different scenarios. And then we basically look at the behavior and say, okay, let me decide, do I yield? If I yield, then I have to come to a point of stopping, and how do I plan my trajectory into that stopping point nicely? So let me check the time. Okay, sorry about that. All right, so that's the 3 kind of model. Let me go quick a little bit. So literally, we want to find a algorithm that do the following. Number 1 is, let's assume the blue diamond is your future point, and you already decided that's the point that you want to enter the highway, and then you generate a lot of trajectories, you check with the constraints. Constraint can be due to safety, smoothness, and so forth. And then finally, you do some kind of optimization and select the one you like. And another important issue to discuss here is that we don't use the global coordinate XY. In fact, we use the Frenet coordinate, which makes our optimization decisions much simpler, faster. Without going into the detail, these are just pictures to show that it's not a rapid random tree, it's not the NPC. We call that deterministic sampling. So you look at the future and you say that I'm sampling terminal time, your Frenet coordinate lateral longitudinal direction. Literally, we are looking at more than 1,200 possible trajectories, and we make the decision. We look at the constraint, and then we pick the one that's the best. So literally, you have to look at the constraint, curvature constraint, and so on and so forth. Sounds very complicated, take a lot of computation, but truth is that we can do everything within 10 milliseconds. Not using a GPU, we just use a computer CPU. And I will just be quick in saying our obviously cost function, see the journey, mobility, drivable area, and safety, and so forth. Let me play this video of you. So literally, we look at the driving inside a imagined simulated MCD. There are many other vehicles, very busy, multiple vehicles driving in every direction. You have a parked car on the right side. In the roundabout, you see another parked car, and so forth. And you always make these multiple decisions of do I go into this gap or not? Do I slow down? Do I drift a little bit to the left? And so on and so forth. Literally, we have found that our deterministic sampling accuracy was able to handle almost all the scenarios we have in a very complicated driving world inside MCT, and very fast. Again, we can control up to about 100 hertz. All right, so obviously we look at many scenarios, roundabout, left turn, and so on and so forth. So we do a lot of simulation, making sure that our deterministic sampling algorithm works very robustly and much faster than other algorithms like MPC and RRT. All right, so I'm not going to play all the videos. Given the time constraint, I'll be, again, trying to keep 5 minutes for questions. I'll be talking about the two remaining problems that I think are also very important. And honestly, we haven't done a lot. So I'm just talking about the current status of two emerging fields. Number one is predicting the behavior of other human drivers. Obviously, the previous motion planning problem, we are using some kind of projection. At this moment, we are using some fixed constant speed trajectory. So, for example, when you look at other cars in the simulation, you assume that you know their speed, and you assume that they will more or less keep the same speed in the next several seconds. Obviously, this is not always true. There are interactions among vehicles, and sometimes they will accelerate, sometimes they will decelerate, and obviously all those will affect your future decisions. So if we can have better prediction of other human drivers' behavior, we can make our deterministic sampling results work even better. So what are the predicting approaches? Again, a lot of people just use the very basic, for example, constant speed, or say average speed. Let's say you look at a pedestrian. It's very hard to measure the speed of a pedestrian. However, you do know that the average walking speed of a human pedestrian is about 4 kilometers per hour, or 1.1 meter per second. You can also, statistically say their fastest speed is about 2.2 meter per second, and so forth. So you can use either constant speed, average speed, or maximum speed, or constant acceleration, or many other ways of predicting their future. The second is that a lot of people also do big data and curve fitting. For example, on the right-hand side, you can see that people actually were using this is a car following behavior. So you can collect a lot of data, and you can try to curve fit and generate some model, and that gives you a better idea of what the vehicle may do given the current range rate, and speed, and so forth. You can predict their future more accurately, even under interactions. The third approach that many people are looking at, and we are also looking at those, are big data, machine learning. And the goal today, if you look at the Waymo competition leaderboard, they are hoping that we can predict the future behavior of other vehicles, for example, a few seconds, right? You can say 4 seconds, 6 seconds, and so forth. But predicting into the future is very hard, but that's what many people are trying to solve. And that's the last problem. The contextual understanding is also a very different and hard problem. That's not what we are working on at this moment. We are looking at the big data machine learning kind of behavior. Again, basic model can look at, your goal is that if you know the current input X, Y, and you want to predict the future behavior Y, which means the future behavior, speed, position, and velocity of other vehicles. When there are interactions, then usually we need to use a neural network. There are plenty of work. People are using long and short-term, neural networks, social and generative adversarial network, and so forth. The key challenges, I'm not going to really talk about a lot about the results because we don't have very preliminary result, is that if you look at the very complicated problem of, say, geometry, people coming to interact with each other, how do you model that behavior accurately, knowing that every roundabout is different, the radius, how many legs, and the travel speed limit, and so on and so forth are different. Not like the long multi-lane, some of the roundabouts have, say, 2 lanes, which is a much harder problem than a single lane roundabout. So we are working on the problem, obviously trying to first collecting a lot of real world data. Second is that we try to find a framework that you can project the behavior of these vehicles into a graph-based neural network. So the absolute X and Y probably wouldn't work, but if you can find a way to describe the relative interactions of the vehicles, and you can use it for any radius or any geometry of the roundabout, that would be great. So again, we don't have a lot of results, but that's what we are working on. The very last topic I will quickly touch upon, and again, this is something that is relatively new and not too many people work on that, is roadmanship. So roadmanship, for example, at the left intersection, let's say you want to make a unprotected left turn. Here is you can see a yellow, flash yellow light. So in other words, the vehicle at the intersection can decide, do I take the gap or do I yield and take the next gap? And that's a decision that may not have a lot of safety implication, but that's an important decision to make. And we want to make sure that we are driving more like a reasonable human driver, not too aggressive and not too timid either. So it's important to understand how human drive in such a situation. For example, if you look at this particular intersection, we first do some bird's eye view projection, and then we use machine vision to measure the relative motion and then try to understand humans' behavior. And the behavior we want to capture is, for example, imagine you are the red car, and there are multiple lanes, and there are red and cyan color cars there, and you want to decide, look at that situation, and do you think that you should yield to both the cyan and orange car, or you should take the gap in front of the orange car? So again, that's a reject and accept kind of decision, and we do have a lot of data collection, and so that's a very heavy lifting machine vision work, and you need to collect thousands and thousands of trajectories, and analyzing the gap acceptance and rejection behavior, and then try to use some kind of model to separate the accept and reject gaps, and then understanding, for example, if you want to follow the behavior of the so-called 50% human driver, which gap should you take, and if you want to be a 25% driver, in other words, a more conservative, or 75% a more aggressive human driver, whether you should take that gap or not. So again, it's really a big data collection exercise, and it's important to know that this is mostly a data-driven research, and rather than there's a lot of theory behind it. And there are many other roadmanship problems. In fact, we think that we need a lot of data and we need a lot of analysis to understand how human drives, what are the proper driving speed, what are the proper acceleration level, proper spacing, especially to vulnerable road users, and what do we mean by unnecessary or too hard of a braking or sharp steering, and how do we make sure that we drive without causing hazards to others, especially vehicles behind to us. So in conclusion, I talk about four things: motion control, motion planning, and motion prediction, and finally, roadmanship. There are still a lot of research questions to be solved. Thank you very much, Yan and Andreas. We may have a couple of minutes for questions.
Thank you so much, Dr. Peng, for the nice talk, and also like give so many great methods to the audience about these problems. So any questions from our audience? So I do have one question. So I'm very impressed by the sampling strategy that you mentioned, at 3 typical scenarios that covers like all kinds of different complex traffic situations. So I have one question regarding how does that sampling strategy handle the uncertainty from the trajectory from the other agent, for example?
Yeah, that's a great question. So at this moment, we cannot really handle a lot of uncertainties. You can basically say we handle uncertainty by almost like NPC, right? It's a rolling horizon. Every instant we solve the future 6-second problem, we choose a trajectory, but we solve the problem again maybe 20 milliseconds later. So in other words, we may be totally wrong about the behavior of other cars, but we will correct ourselves next sampling instant.
Yeah, that makes sense. Another follow-up question is, for example, during the lane change, let's say we are in the middle of lane follow and lane change essentially. How do we actually make that decision during that period? If, for example, if the adjacent vehicles that behind our ego, originally we plan to use that gap, but suddenly the intention from that car changed. During that process, how do we make that decision from those 3 typical scenarios?
Yeah, thank you. So obviously that's a hard problem. Like a lot of time we try to say that's a gap I can take, and then the car behind suddenly accelerate and the gap suddenly become much smaller, and then you may need to abort. Right. So yes, a lot of the time this is what we do. We look at the future for 6 seconds. We plan and we say this is how we drive, and situation may change, and you may actually look at the situation and say either you accelerate and take the gap still, or you actually abort and come back to the original lane. All of this will be coming from the, again, future trajectory plane, just like what the NPC does. Again, I don't think there is a very rigorous robustness analysis, but by the fact that it's a rolling horizon, you only implement one step, and then you will reassess. When it's not safe to do so, you will abort.
Yep, got it. Thank you so much.
Right.
Can I ask a quick follow-up question? So is it possible that this kind of rolling horizon planning will lead you to some inevitable failure because of the a short over period horizon?
So obviously we all know that nothing is totally guaranteed, right? Even NPC, can you suddenly run into a situation that you have even instability issue and so forth. So I don't think we have a true guarantee for any method per se, and that's why we always have a so-called MCT safeguard. So it's almost like your Windows may crash, your app may have some problem, but you always have a bias underlying. We call that safeguard. So safeguard is very different from your intelligent chauffeur algorithm. So path planning is a chauffeur, right? But your safeguard is your safeguard. So if you say, oh, I have some unforeseen problem, safeguard may be the one that save you.
I see. Cool. Great. Thank you.
All right. Thanks.
Thank you so much. Really, really helpful.
I think there is another question in the chat.
Yeah, sure. So from Daniel, he asked, currently 6 seconds prediction is a goal. How many seconds in the future would be ideal for a mass development for the self-driving vehicles?
So obviously 6 seconds is not the rule, or there's no strong reason to choose 6. In fact, when I was a PhD student, right, we always argue that if you can preview into the future by half a second to 1 second, it's already very, very helpful. So if you only look at instantaneous versus you can preview 1 second, you can be so much better already. Now, so do we really need 6 seconds? I don't know. I don't think I have a rigorous number to say. So thank you, Dean, for yielding a few 2 minutes to me.
Thank you so much. Yeah, really nice talk. And next, we will have a new talk from Dr. Zhao Ding. Dr. Zhao Ding is an assistant professor of the Department of Mechanical Engineering at Carnegie Mellon University. He's also with Robotic Institute, Machine Learning Department, SciLab, Manufacturing Future Institute, and Scott Institute for the Energy Innovation. He is recipient of the U.S. National Science Foundation Career Award, the Carnegie Bosch Research Award, and Strominger Teaching Award. Welcome to join us, Dr. Zhao. Really looking forward to your talk.
Yeah, thank you, Yan. So thank you for all the organizers to give me this opportunity. So today I will present a topic on generating driving scenarios for better algorithm design and evaluation. Okay, so there's a lot of topics, but I will basically talk about some interesting ideas that we have done during the years. So first of all, so the concept of scenario, especially traffic scenario, is not precisely defined. So historically, we have, DOT has started the typical driving so-called pre-crash scenarios from some collision data set. Here you can see they list the top 10 scenarios, and I illustrate them on the right. It could be car following, lane change, and something else. So this is how we do that previously. Well, there is some limitation about this kind of definition, because first, the scenarios are manually selected by human. At least the definition should be first defined when you look at the when we look at the data, and then after we check the data, then we actually try to count how many scenarios happen for one particular collision. Then we decide which one will be most important. But eventually, someone need to define the scenario first, and also. The human and the autonomous vehicles could have very different critical scenarios. So usually it will be very risky that we deploy autonomous vehicle on the public road and hope that everything will happen as the same as how the human handle what human will encounter. Because there is a certain difference between the behavior of autonomous vehicles and a human being, and maybe people also react to them differently. That being said, this method has been very successful in the past decades. For example, Euro NCAP has used this to test some active safety systems. But I think, given that we already collect many companies have already collected a lot of massive data set. So that probably can do a better job. So if we want to generate realistic safety critical scenarios, there is, as I said, some very good opportunities, but there are also some challenges. Opportunities, for example, we have like more richer data. We have more powerful computational resources. And also we arguably, we have a better machine learning algorithms. And also, but still there are a lot of challenges, including, so the data we collect from the real world is usually very sparse and also imbalanced. And for safety critical events, they're rare. And usually there are multi-models or multi-modes. So here, what I mean is by saying that for safety critical event, there are a lot of different kinds of them. And they can be clustered, but they are not necessary. You can infer from one to another. And also, driving is a dynamic, long horizon temporal decision making process. So it's a sequential data that makes the data set itself is a very high dimensional. And in addition to that, some data is in the form of images or LiDAR point cloud. So that make also, each frame is also a high dimensional input. So all those can be challenging, but we also have some hope. So to create safety critical scenarios. So some of my previous work that actually I work with the previous speaker, Professor Peng, who is my PhD advisor. So we work together on this accelerating automated vehicle testing that we want to emphasize on those scenarios that are risky and also has a maximum likelihood of occurring. So to achieve this goal, to achieve the accelerated test, we actually have we need to satisfy two conditions. So one is we want the most likely fail of failures of AV, and also this scenarios will be most likely happen in the real world. So we need to satisfy two conditions. So one is the likelihood of scenario in the real world should be to get the likelihood of the scenario, to assess the likelihood of the scenario in the real world, we need to have a model of the real world data, right? So we need a model to model the real world driving situation. Second, we want also to increase the likelihood of the failure for the ego vehicle. In that sense, this is a AV ego vehicle dependent problem. So we also need the ego vehicle to be tested in the loop so that it should be adapted to it to make this testing more efficient. So we can use simulation, we can use a physical engine, physical test setting. So basically that's a two case. And to satisfy this two is non-trivial, and we have we have spent many effort on it to try to solve it. The general idea is actually pretty straightforward. That is, we just model the naturalistic environment. You see this on the left. Most of the time the car is far away, and the relative distance is relative speed is small. And when we accelerate this environment, most of the time is much more collision, but not unavoidable collision. This more like what we call the near miss, that we still is very risky, but sometimes it's just like a very risky, but still have a higher chance to occur in the real world. So we are not simulating that situation that the car collide to another car unavoidably, because that could be too rare. Right. So then this is also a work we have on the MCD previously, and we use another vehicle one vehicle as a background vehicle to test the other vehicle. For example, in the similar situation, just in the previous simulation, this is the real world version for that. So the ego vehicle trying to cut in front of another vehicle, and the velocity, the relative velocity and speed is controlled by these two conditions: the model of the real world and the learning model of the car to be tested. Right. So, but there is a limitation for this method. It's obviously that we need a model of the real world to estimate and sample the scenarios, right? So how we can model the real world? If this model is inaccurate, then the whole analysis will be inaccurate as well. So this is come to a so-called generative model or density estimation problem. Okay, so how to do that? This is say, given we have the model of the real world, we can accelerate and find the critical scenario, the near miss scenarios. However, how to model the real world? And one obvious way that people have studied is more like a generative adversarial network, or something else with or VE that depends on neural network. So we'll also explore this direction. So the challenge of doing this is, first, as I said, this is a sequential data. So suppose we have two trajectories. We have two trajectories. That is, one trajectory is one car, another trajectory, another car. And we can encode these two with a autoencoder. And here we use a bidirectional GRU, so module to encode these two trajectories so that we can learn their relationship. And then we can sample it and use reparameterization. And then we can do the decoder and output a trajectory that are with the same distribution as original data. So this is one way we can generate the data set, a bunch of data set. So here you can see we actually, with some input, and we can design this neural network. Then we can populate the data set by generating a lot of new interaction between two vehicles. Right. So yeah, so this is one of the first paper study the generation of interactions using deep generative model. But there is also limitation about this idea. So first of all, we only study the trajectory. We didn't consider the road information. We could generate some trajectory, some interactions that no real world road actually has this shape. So this is the one limitation. Another one is we cannot guarantee that the generated results are safety critical. Actually, there is no guarantee at all because we just learn from the real world and we generate the trajectory. So how to control the rarity or severity of the generation, that's unknown. So one idea that we use to solve this problem is a updated version of the first idea. So the idea is very interesting. Is okay. So suppose we have this naturalistic data set that we used before. Suppose we have another data set. It's a collision data set. So that could collect in simulation or just artificially design. Actually, US DOT and the German Department of Transportation, they all collect some data in the real world for collisions. I think in the future, once we have more and more cars have the data recording capability, we can collect more collision data. So suppose we have this additional collision data set. Then the idea we have is, can we design another neural network to combine these two data set and generate something in the middle, while also conditional on the roadmap we get from these two data set. Okay, so the idea is this. So that's how we design the neural network. It's turned to be very effective. So we have a lambda that we use to control the weight between the learning between these two, the weight of learning between these two data set. When lambda is 0, that means 100% safe. When lambda is, we just learn from the safe data set. When lambda is 1, that means we fully learn from the collision data set. So all the trajectories, interactions are collisions. By tuning this lambda, we can actually control the the severity of the scenario. And also because this is a conditional Huei, so we can conditional on the environment, the road condition that we collected from both data sets. We can say we want to conditional on particular road and generate this scenario. So this is how we do it. And in this case, we can not only generate the scenario that follow a particular road we desire, we want, and also we can control the severity. And there is something else that need to be improved. So one is how here is like multi-model adaptive risky scenario. So a lot of case, the machine learning, the GAN or deep learning model may just convert to a local minimum. So in that case, they will only generate one type of risky scenario, because that gives you the maximum likelihood. But that will ignore all the other all the other problems, all the other collisions, type of scenarios. How we can diversify this study? So that's another problem we face. So in this case, we particularly design a car with the interaction with the cyclist, and we have, for this particular scenario, we designed the Bayesian like a graphical model that capture this environment. So for example, in this case, we can generate the cyclist that goes through different directions and interact with this car. You can see there's many ways that this car may collide into this cyclist from on the right or on the left. Clearly, this is not a single mode learning. It's actually multimodal learning. How to learn all those different kinds of collisions. So that original deep neural network is not enough. So this is the standard way that we use a normalizing flow model to learn the distribution. So that's the first step. But the key idea is we add a adaptive sampler. The idea itself is very straightforward. That means the adaptive model basically learns how familiar we are with one type of collision. If we got very familiar, so they have a score for this local minimum, and that will bring down the importance of this local minimum. So the algorithm will jump to another local minimum. So that will explore and find another collision. So this is the adaptive sampler role. Okay. And also, as I said, we also want to not only find the weakness of the car, we also want to find how likely this scenario will happen. So we also want to increase that too. In this case, we got data from Argo words, and when we design the general model, so we also have a weight for the likelihood of the appearance, the behavior of the cyclist. So we balance these two, and actually these three: the failure of the car, the likelihood of the behavior, and the familiarity of us to one particular local minimum. So that's these three combined together, we design this model. That's our objective function, and so that we can jump from one collision to another. Right. So this is great because we can use this to evaluate a lot of autonomous vehicle designs. Right. And then we actually use this to evaluate some autonomous vehicles that were trained by reinforcement learning. In this case, we trained the autonomous vehicle with 6 different types of reinforcement learning: DQN, SAC, A2C, PPO, DDPG, and MBRL. And we compare them with our environment. And we found actually something that we have never seen before. For example, some algorithms, they may behave very well if we just use a normal environment to train and test it. But actually, if we're using our environment to generate the risky scenario for those algorithms, some reinforcement learning algorithm will become very unstable. So that being said, so because most of the time the reinforcement learning paper, they just use Monte Carlo to test the algorithm for their performance and robustness. In our case, we actually provide another alternative that you should also consider to design a more challenging scenario and more diverse scenario to test the reinforcement learning algorithm. Okay. So also another idea is the interpretability of those scenarios. So here we and one key question is how we can control the granularity of this scenario. So like how coarse is the scenario? We can just say all the scenario can be collision or non-collision, but that's too coarse. But we can also have each thing could be a scenario, but that's not very useful. So we need to consider maybe a rigorous way to define the numbers of how many types of scenarios that could be more scientific. In this case, we call the traffic primitive. We use the unsupervised learning, particular Bayesian non-parametric, to decide how many scenarios we should decide to test autonomous vehicle is proper. One example is here is we use the safety data set from safety pilot data set from collected by University of Michigan. Here you can see the different colors represent different types of clustering that we found for vehicle-vehicle interaction. And you can see on the highway, it's almost the same color because it's almost the time car following. And in the section, actually, in the intersections, there are actually many different colors. So that will represent there is many different kinds of interactions. So Bayesian non-parametric is actually a mature unsupervised learning algorithms that has been used a lot. So the key idea is that usually people do unsupervised learning, they have a k-means, right? So the k is fixed, but the Bayesian non-parametric, the k is actually sampled as a random variable. So we sample k to get the best of the biggest likelihood, and then the eventual k will be the optimal k to decide how many type of scenarios that we have in the real world. So yeah, we also do something crazy. This is a video that from the YouTube. This is in Ethiopia. You can see this is a very crazy intersection with a lot of cars running different scenarios. And we ask ourselves a question that if we are the designer of a autonomous vehicle that want to run in this area, then how many scenarios we should have? So this is the ultimate test we can imagine to test our algorithm. So the very challenging part is the number of surrounding vehicles. The number of surrounding vehicles is time varying, right? So it's always change. So what we do is we just apply, the unsupervised learning, the Bayesian non-parametric method I just mentioned before, the same method, except we have some lot of pre-processings, including some vision, some tracking pre-processing, and also we model things with a Gaussian process instead of just neural network. Then we can have a fixed dimension of data to study. Then eventually we conclude that there is 6 main ways that a car may interact in this situation, right? So these are the 6 colors are listed here, and those arrows means how other car may run surrounding this vehicle and described by Gaussian process. So yeah, so this is I think the craziest way we can think about how many scenarios we should define in a very complex situation. Okay. And we say, okay, so then come back to my original question. So what if I want to design an autonomous vehicle with this information? Can I leverage this scenario concept to design? The answer is yes. So we also published a paper on this last year. So this is on the left, this is how we design a traditional model-based reinforcement learning. But we actually have defined the dynamics with the Gaussian process, like a dynamic directed process and Gaussian process approach, so that we have a sample the number of scenarios we have in a complex situation And next time, once we have a new scenario, we'll first check whether that has been seen before. If not, then we identify that's a new scenario and learn a model of it. If it's the scenario we have seen before, then we just use the scenario we already learned. So this is a much efficient way. Actually, this can be a like online real-time reinforcement learning algorithms. And because we are using Gaussian process model, so that's actually can be interpretable well. We know which scenario didn't do well if eventually, if the score is low. Okay, we test that in the Hafshita environment, like OpenGym environment. Also, we test that in the like intersection environment. Because in the intersection, there are actually many ways the car will interact with the other car. But also there's kind of limited ways. There's not like continuous way of dynamics. So that can be, we believe the scenario can be clustered. Okay. So finally, I just want to mention that our study that, okay, so we talk all of this, but the key idea is that we either make assumption we have a collision data set, or we make an assumption that we have some prior knowledge. For example, we know the scenario can be clustered. But what if we have some rules? For example, vehicle dynamics rules, traffic rules, and other rules. Can we use these rules, embed those rules in the deep learning scheme? So this is what we do to design LiDAR point cloud scenes, and use that to generate adversarial examples to perception system, to vision system. This is very challenging because you can see the point cloud is actually very, very high dimensional. So how to generate the very complex scene that can attack the state of art LiDAR object detection algorithm. So this is the rank on KT dataset for all the LiDAR point clouds. We actually pick 4 of them. They're just invented like a few months ago. So the key idea is that we use a tree. We use a tree VE so that the VE can generate the tree structures, different tree structures. And in this tree structure, we actually enforce the node level knowledge and the edge level knowledge. So the knowledge actually can be the knowledge can be, for example, the road should follow a given layout, and the vehicles on the same lane should have the similar direction, have same direction of the lane, and the vehicle should be gathered together, but keep a certain distance. So there are very simple rules. But once we get this rule, this can dramatically help to increase the efficiency of searching and generation for this high dimensional point cloud. So we compared with some perturbation method, some post perturbation method, and our scene attack can not only propose a very effective attack, but also can generate scenes that looks very realistic. For example, compared with this pose attack that they placed a car everywhere. I think this is how we embed knowledge into the scene generation. And also interestingly, we find out that the adversarial scenes we find in this case actually have a very good transferability feature, so that they can not only attack if one, they can compare with the other method, point attack method, that our method can transfer to, and if the one adversarial scene for one LiDAR point cloud algorithm should also be the adversarial scene for the other algorithm with a relatively high probability. Okay, I think that's how our long journey about scene generations for safety critical events. And I want to thank you for the audience.
Thank you so much, Dr. Zhao, for this comprehensive study and also share with us all the studies on the generating things. And I learned so much. One question, how do we know that the, let's see, the stack of autonomy is safe enough to deploy into the public route based on all your comprehensive evaluation and scenarios?
Mm-hmm. Yeah, so I think first someone need to define what do we mean by safe enough, right?
Yeah, totally agree.
Yeah. If we say the safe enough means we are safer than the current statistics of human, then I think then we have a particular bar. And then secondly, we need to learn how the car will react to different scenarios in the real world and what their likelihood to success or failure. So suppose we have 1,000 scenarios that we identify, and they have some weight of those scenarios will occur in the real world. Then we can just do the permutation and test the car for the 1,000 scenarios. Of course, this is maybe infeasible sometimes if for the physical car. So I think nowadays, as long as I know, many autonomous companies are put a lot of effort in simulation, and they make a lot of progress on that. And in simulation, I think the key technology for simulation, in my opinion, is this what I present, like one of the key technology I would say. It will be like how you can generate the moving scenario, because make a simulation for static object is actually kind of already solved. Maybe another one is like a sensor modeling, but that's another problem. Yeah, that's another question.
Yeah, thank you so much. I totally agree with you. I think this is super, super critical for the whole industry to actually deploy autonomous driving into the real world in a scalable way. Thank you so much for sharing that. Any questions from our audience?
There is a question.
Yes.
Since the ego car will also be part of the function, the scenario identified were very okay. Yeah, so that comes back to the definition of the testing, and there's many argument about fairness of between tests. So some say you need to give the same test to everybody to make it fair. I think that's not true, right? So you give the same exam to anybody like who are like a basketball player, who are a football player, so they may perform very differently. But eventually, I think we still need to have a particular likelihood for each scenario. So yeah, so in my opinion, I think the ultimate goal is to say we want to know this car deployed to the real world, then how many collisions they will have. That's ultimate correct goal. But you may want to design a fixed scenario to approximate it. And whether that can be, if you have more information of the ego vehicle, you may have more better accuracy. But that may not be realistic. So people need to some kind of approximation.
Got it. Thank you so much again for the talk and also the answers for all those questions. Next, Dr. Changliu will give us a talk on the learning and coordination for the autonomous driving. Dr. Changliu is an assistant professor in the Robotics Institute, School of Computer Science in Carnegie Mellon University, where she leads the Intelligent Control Lab. Dr. Liu published the book on designing robot behavior in the human-robot interactions in 2019. Dr. Liu also received Amazon Research Award. Welcome, Dr. Liu, to join us. Looking forward to your talk.
Thanks for the introduction. Actually, I do have several questions for Dean, but I'll leave it later. And it's very impressive to see that very complicated intersection can be reduced to 6 kind of scenarios. That's very interesting. And today my talk, is on a learning and coordination. That is our recent work in an attempt to address uncertainties in autonomous driving. So let's first talk about some of the background. So our goal is to make sure that autonomous driving will be safe and efficient. But actually, it seems we're not there yet, because there's some trade-off between the safety and efficiency when there's uncertainty. For example, this is actually a quite old video. And we've seen another video from Dr. Peng's talk in this video, the autonomous vehicle actually unnecessarily yield a car, this one, which it does not have any conflict with due to the uncertainty, and that creates the conservativeness and inefficiency. But if we look at human driving situations, so this is not the crazy intersection that Ding just showed. This is a normal middle-sized intersection at Shanghai where I took when I go back to China. It's not the car, there's not so many cars, but the human drivers are able to like cross each other without slowing down, and so it can do this both safely and efficiently. How can we make the autonomous vehicle do this? It's a key question we want to address in our research. And we believe the major difficulty is that for autonomous vehicles, it has a lot of uncertainty in predicting what will happen in the surrounding traffic situation. And because of that uncertainty, the behavior of the ego vehicle is being inefficient. So our recent focus is on how can we minimize those kind of uncertainty, either through learning or through coordination, so that the behavior of the autonomous vehicle can be more efficient while guarantee safety. Yeah, so an overall framework is that we want to design the behavior of the autonomous vehicle to be both efficient and safe while facing all the design constraints. One is there's uncertainties in the environment, and there's computation limits. And then we use learning and coordination to address the uncertainty. We also did some other work in terms of addressing the computation limit by developing more computationally efficient optimization algorithms so that our complicated algorithms can be run in real time on embedded system. But I'm not going to talk about that in today's talk. I'm mainly going to focus on how we use learning and coordination to address the uncertainty. So before we dive into technical details, I would like to provide an overview of the framework that we use to tackle the problem. So we modeled the autonomous driving for a single vehicle as a multi-agent interaction, where the ego vehicle, as the red one, is surrounded by some other autonomous vehicles or human-driven vehicles and some human pedestrians. And every vehicle and every human pedestrian will be viewed as one agent. Every agent has their own dynamics. And then the ego vehicle has the sensors to sense the state of all the agents in the environment. And then the sensory information will pass through the control system. The control system will make a driving decision. Meanwhile, all the other agents in the environment has their own sensors and then their own control systems. And our goal is to design the control system for the ego vehicle. And this control system is a mapping from the data we get from the sensors to the action that we apply to the hardware. And usually this mapping can be called as a control policy, control law, which is, in our framework, we use model-based control. So it's a condition mapping, which is conditioned on the cost function for the ego vehicle, and then the model the ego vehicle has for itself as well as for others. Like it uses the model to predict the future behavior of other road participants. But those knowledge may not be accurate or may not be fixed while the vehicle is interacting with the environment because the system may evolve during the interaction. So we also need to have some learning module to either update the knowledge or update the control law directly. And in our control system, the control law is actually solving this constraint optimization, which minimizes a cost function for task performance and the motion efficiency, subject to the following constraints, where the first line of the constraints are the constraint for the ego vehicle, like the dynamic constraints and the feasibility constraints, which constrain the control of the ego vehicle, the state of the ego vehicle, and then use the ODE to describe the dynamics. And the most challenging constraint is actually the constraint from the second line. That is the safety constraint during the interaction with the surrounding environment, where this XR is the state of the ego vehicle, XH is the state of all the other surrounding road participants and also some environment state. And then we need to make sure the ego vehicle always stay within a safe set with respect to the state of the others. So in this like a cartoon here, if our ego vehicle is this gray one, then the goal is for it to drive safely by avoiding all the surrounding vehicle. But this constraint is actually very difficult to deal with if we solve this problem into the future. That is mainly because we have model uncertainty. That is, it's very difficult to accurately predict the future trajectories of all surrounding vehicles. And also, if we have we have sensor noise. And so in this case, the current perception or current state of the other vehicles may also be not so accurate, contain some noise. And if we do this planning into the future, the uncertainty or the noise may accumulate, which will result in the conservativeness that we saw earlier in the video. Yeah. To see the conservativeness better, we just use one example here. Suppose we want this robot to move to this target in this confined environment by avoiding this human. What the robot do is to first predict the trajectory of the human with some uncertainty corn that will grow with respect to time, and then plan a trajectory, and then execute this trajectory, and then do a prediction again with some uncertainty, plan a trajectory again, then execute a new trajectory. And this is the typical NPC-based planning. As we can see, because of the uncertainty, the robot behavior is very conservative. Definitely, we can have other approaches to break this conservativeness. For example, breaking the planning into some long-term planning and some short-term planning so that we can reduce the uncertainty corn. But fundamentally, we should still try to minimize the uncertainty corn here so that the robot behavior or the vehicle behavior can be more efficient. And in order to minimize the uncertainty, our current research focus is based on two approaches. One is active online learning in order to address uncertainty in real time. And the second is to introduce coordination through communication. Okay, so the first part is using learning. So typically how we do learning to learn prediction models for like traffic behaviors. The usual pipeline is like we first collect a bunch of traffic data and then do model learning. We can use whatever models we like, and then the whatever learning algorithms that can help us identify the parameters in the model. And finally, we get this kind of prediction model. It can help us to either predict the intention of the surrounding vehicles or directly predict the trajectory. Once we get this model, we can then input the real-time measurements to the model. Then the model will tell us the prediction, like several future trajectory of the surrounding vehicle in several seconds later. So this pipeline works in practice, but the major challenge comes from the distribution shift between the real-time measurement we can get and the training data we get. That is, we probably get a lot of training data from the NGC data set, and then we want to deploy the model in some new traffic scenario, maybe in China. Then the traffic pattern is totally different. How can we deal with this kind of traffic shift? Definitely, we can collect more data in the environment that we want to deploy the model, but that's very expensive to do that. If we do not have the luxury to get a lot of data, how can we deal with this distribution shift? And our insight is that we can introduce the notion of continual learning or online adaptation of our offline learned prediction model in order to minimize the uncertainty. One thing I forgot to mention is that if we anticipate a distribution shift, then in order to stay safe, we need to enlarge the uncertainty zone in our real-time prediction, considering the distribution shift. But if we do the continual learning or online adaptation where we can minimize the prediction error, then the associated uncertainty can be shrunk to an acceptable level. So how can we do the model adaptation? It's actually very similar to the system identification in adaptive control. And here we just illustrate this process using this diagram. We have the ground truth dynamics in the first row, where X is the vehicle state that we want to predict. the model, ground truth model is assumed to be xk plus 1 equal to fxk. And then we have a prediction model parameterized by theta k. And at k minus 1 step, we have a parameter estimate as theta k minus 1. And we use this parameter to get a prediction. And in the next time step, we get the ground truth measurement for xk. Then we compare this ground truth measurement with our prediction. And we get a prediction error, and then we let the error go through an adaptation mechanism to turn the error into some update signal on the model parameter. Then we can get the new model parameter theta k. And then we can use this new model parameter to get a new prediction. And we can keep doing this process again and again. So at every time step, there are just two computations. One is to get the error from the prediction. Then second is to turn the prediction error into the model update signal. So if we write down the mathematical equation, the update rule is something like this, where the theta k equals to theta k minus 1 plus some learning gain, multiplying the gradient of our model, then multiplying the prediction error. And this framework can be, this computation can be done using standard stochastic gradient descent or our favorite recursive least square for adaptive control. So we have applied this method in a wide variety of models. For example, this slide is showing the online adaptation of a vehicle prediction model learned using a multi-agent imitation learning algorithm called parameter sharing Gale. So in the left figure or left video, we're showing the performance. So the ground truth is the blue curve, and the originally learned PS Gale is the green curve. As we can see, it has it's not very stable and also sometimes have big error. And then after adaptation, the red curve, the prediction performance gets much better. And also this algorithm can help track multiple vehicles in the traffic flow. And how does the error profile looks like in this online adaptation scheme? It is shown in this figure here, where the horizontal axis is the time steps and the vertical axis is the prediction error in meters. So in the beginning, in the near future, the error is usually very small. The prediction error grows exponentially as time proceeds. So in the beginning, we have an error profile like this green dots. And then after several steps of adaptation, we can see the error profile gets sufficiently depressed to some acceptable range. Yeah, so in this case, it demonstrates that this online adaptation can efficiently help us minimize the error in real time, and then as a result, minimize the uncertainty that we need to consider in our planning. Yeah, and in terms of the, algorithms, which algorithm works the best for online adaptation, we have tested a variety of adaptation algorithms. So for example, gradient-based first order methods, representative methods are SGD, ADAM, or AMZ-GRED, or second order methods using least square, for example, recursive least square, extended common filter, modified extended common filter. And empirically, we see that second order methods in general performs better than the first order methods. These are also intuitive. That is mainly because second order methods follows the Newton update rule. And it's well known that those kind of Newton optimization has faster convergence when you're already closer to your local optimum. And because our neural network is well trained offline using the existing data set, even in the case that there's distribution shift in the online scenario, the shift is not so big. So the actual optimal is still very close to the parameters we get offline. And in this case, if we use the Newton-based method, it can efficiently find the local optima online and then improve the prediction performance. And also in terms of which model we can use or we can apply this kind of adaptation, there's actually no limit as long as we can take the gradient then we can apply this method to any kind of model. We have applied it to linear regression models, deep neural networks, recurrent neural networks, and also graph neural networks. And also in some cases, especially during the online intention prediction of the surrounding vehicle, it's possible that we don't have the direct ground truth measurement, if when we are doing the prediction. In this case, we can develop a multitask model that it generates both trajectory prediction and intention prediction. Then we use the ground truth trajectory to adapt the model. So that's the intention prediction. In our experiment, we see empirically intention prediction also gets improved. Okay, so that's one method that we introduced to improve the prediction accuracy. And we are also exploring some other methods. That is mainly because this online adaptation, although it can help improve the accuracy, but the data flow is out of control, out of the designer's control. It actually is generated in real time. So if the adaptation goes unstable, then that will still create safety hazards to our system. So what we are currently exploring is that, is there a way for us to introduce some offline methods? For example, actively augment our dataset offline in order to make sure that our prediction model covers a wide variety of situations. So this is a very preliminary work. And our idea is that we actually need to add data that is most confusing to our model. For example, data on the current decision boundary of the model. And after we get those kind of data, we can ask the human expert to label the data in order to obtain more information. So for example, if we want to do a 2D classification, as shown here, and we get a bunch of data, then we get a learned model, which apparently does not quite mimic the real shape here. And then what we can do is to try to find the points on the decision boundary here and try to get the label for these points. And by doing that, we can expect that the learned model can gradually converge to the ground truth. And this way, because we have a targeted direction to add more data, so it actually improves the data efficiency. So it can learn the model better with the same amount of data without this kind of active probing. We have tested this approach for human motion prediction, and we're currently testing it on the vehicle prediction. We don't have the concrete result yet, but for human motion prediction, we do see very good performance. That is, with this kind of adversarial data augmentation, we can make the training accuracy continuously grow, while the other approaches may saturate. Okay, so that's the first approach, using learning to address the uncertainty. And but the learning sometimes can also have its own limitation. That is the problem of symmetry. So consider, and usually symmetry can lead to deadlock. So consider a situation of this four-way unmanaged intersection where we have 4 cars designed similarly, and they arrive at the intersection at the same time. So there's no priority among them. And then their behavior is done as if, I don't know who should go first, then I should go forward, inch forward a little bit and see the response of others. If others yield, then I should go. If others do not yield, then I should stop. But if other vehicles are doing that, then the system can be trapped into a deadlock that they will yield and stop, yield and stop. Yeah, the main problem is the symmetry across all the vehicles. And in order to break this kind of symmetry, learning is not enough. We actually need to introduce some communication mechanism to allow the vehicles to figure out the passing order even before they arrive at the intersection. And usually for this kind of communication-based distributed conflict resolution, there are 2 kinds of methods. One is graph-based, the other is trajectory-based. They use different information and they use different strategies to break the symmetry. So for example, for the graph-based, only the high-level intention is communicated. And the strategy to break the symmetry is to resolve a conflict graph. And then for trajectory-based, the actual trajectories, continuous trajectories are being communicated. And to resolve the conflicts, we can just do a distributed optimization in the continuous space. So we have explored both methods, but we do observe they have their own pros and cons. So let's maybe first talk about the graph-based method. So in this n vehicle situation, all the vehicles are assumed to be able to communicate with each other. And then we just look into the details of vehicle I. It first has a receiver to receive all the information from others. Then it will use this information to do a decision making on when it should pass the intersection. And how to make this decision, it's based on this resolution of this conflict graph. So we break the intersection area into 4 conflict zones. And if 2 vehicles will occupy the same conflict zone at the same time, then there's a conflict between the 2 vehicles. And then that means there's a link between the 2 vehicles. And then we want to make sure that the passing order is decided such that there's no loop between any 2 vehicles. And how do we decide the passing order? For now, our strategy is a first come, first serve. So we ask other vehicles to broadcast the time expected to occupy each conflict zone. For example, vehicle 1, it will broadcast that it will occupy the conflict zone in C1, C2 in these frames. And then for vehicle 2, it will occupy C2, C3, and C4. For vehicle 3, it will occupy C3. For vehicle 4, it will occupy C4, C1, and C2. Then based on the first come, first serve, we can check the situation in each conflict zone. Then this vehicle 4 needs to yield vehicle 1. And then vehicle 2 needs to yield vehicle 4. And the vehicle 2 also needs to yield vehicle 3, although they don't have explicit temporal conflict, but in the graph, we still ask it to yield. So in this way, we have formed a directed graph where there's no loop. And with this directed graph, we can assign the passing time for each vehicle. And with this passing time assigned, each individual vehicle will use their own motion planning methods to find a trajectory that obeys the temporal constraint. For example, for vehicle 1, it needs to pass this conflict zone in certain time frame, as shown in this white area. Then it can plan a speed profile to do it. And the actual passing time will be computed and shared or broadcasted to other vehicles. After one time step, the vehicle has traveled along its speed profile. The constraint may be changed during the interaction with others. Then the vehicle can plan a new trajectory and then broadcast the new time of occupancy and keep doing this again and again. And once this trajectory is computed, it will be sent to low-level controller to track. And then the time of occupancy will also be broadcast to all the other vehicles. So in this, using this method, we can make sure that all the vehicles can properly resolve conflicts in a distributed manner. As see here, we have a 4-vehicle intersection. And at the beginning, we only have 3 vehicles, but their time of occupancy overlaps. And then using this mechanism, we can resolve the overlapping. And suddenly there's an emergency vehicle, green one, comes in. And then using this mechanism, we can also make sure that all the other vehicles can give way to this emergency vehicle. Yeah. So there are actually different methods to design this conflict graph. The one we introduced is the region-based. They are also vehicle-based. And also there can also be region and vehicle-based. But they have one common limitation, that is their accuracy is limited by, or their efficiency is limited by the resolution of the discrete graph. In order to make the distributed conflict resolution more flexible, we are currently exploring trajectory-based conflict resolution. That is, we're not constrained by any conflict zone. The vehicle can flexibly adjust its own trajectory in order to avoid certain conflict. And this can be done using a distributed optimization framework, which here we choose to use the ADMM. Yeah, so, but also there's another challenge, that is the online optimization is actually very computationally expensive, especially when there's collision avoidance constraint, because in this way, the problem become non-convex. And then we leverage our computationally efficient optimization algorithm through convexification. This is called the convex field set algorithm, where we locally convexify the problem and iteratively solve the trajectory optimization problem in order to make sure we can achieve faster convergence. And this method has been tested in a lot of scenarios, and it can at least improve the computation efficiency for an order of magnitude. So in this way, we can ensure that the motion planning problem can be solved in real time. And then with this kind of distributed trajectory-based conflict resolution and with the real-time optimization, we can allow multiple conflict resolution in diverse environments, which may not be achievable if we use graph-based methods. So this includes like unstructured environment, plateau formulation, merging, overtaking, and all kinds of scenarios. Okay, so since we're out of time, let me quickly summarize all the contents here. So in today's talk, I mainly discussed two approaches to minimize the uncertainty and improve the efficiency while guarantee safety of autonomous driving. The first approach is to enhance the learning. So we can use two approaches to enhance the learning. One is to do continual learning online by adapting the model continuously. And the second approach is to do data augmentation through the training process. And the second approach is to second big approach is to do the coordination through communication, where we can either do graph-based or trajectory-based. Yeah, so that's it for me. Thank you very much.
Thank you so much for the awesome talk, Dr. Liu. Any questions from our audience? Yeah, we do have one question from Huei. So is the persistent excitation condition required for model adaptation in this approach? If yes, how to guarantee this condition?
Yeah, so that's a great question. So in adaptive control, we do need persistent excitation in order to make sure that the parameter converges to the ground truth parameter. But in our adaptable prediction, we actually do not need this requirement. Why is that the case? That is mainly because we have way more parameters than the degree of freedom in the prediction. So we only need to make sure that the prediction error get minimized. Even if the parameter is not the converge to the correct one, as long as the prediction get minimized, we're good to go.
Cool, that's really impressive.
I have a question, Jan, for Changliu. Great talk, Changliu, very interesting approach. I have actually two questions. The first question is regarding the trajectory-based optimization. How do you handle uncertainty of the communication between the vehicles? So each vehicle has, derives its own trajectory, but there's some uncertainty based on the GPS location, based on the communication. How do you handle that in your approach?
That's a great question. Honestly, we didn't consider that effect in our current approach, but that's definitely something we need to consider, especially the measurement noise, the communication delay, and also some adversarial attacks in the communication channel. And we believe one approach to address that is to somehow enlarge the safety margin to account for like a acceptable disturbance. Yeah, but for unbounded disturbance, we also don't have a good approach to do it.
I see. Yeah, I mean, This makes totally sense. The second question I had is that you mentioned that you're trying to locally convexify the problem in order to address, because this is highly non-convex problem, and this is a very interesting approach. I was wondering, are there any implications of this approach to the global optimal solution? How you guarantee that even if you locally convexify this, at the end, you would get the same global optimal solution that you would get otherwise?
Yeah, there's no guarantee that we can still get a global optimal solution. There's only guarantee that we can at least get a local optimal. But in this situation, and also the quality of the local optimum highly depends on the initial reference we give to the solver. So the solver mainly guarantees that we will always find a good enough solution that guarantees safety. But if we want that to also improve efficiency, then we need to have some better strategy to construct the reference.
And this again makes sense. I mean, at some point, it is what it is. We need to, once you get to a real-time implementation, the theory sometimes, we have to, put it aside, and we need to make it work. And but I was wondering, do you plan to have, sort of come up with any bounds that you can at least theoretically bound your solution, saying, okay, I might not be able to guarantee an optimality, but I can theoretically describe that I'm that far away, or something like that.
Yeah, that's a very good suggestion. We haven't thought about it in that way yet, but I think that will be an important or interesting direction to explore. Although it may be challenging because non-convex problems has so many local optimas. It's even difficult to illuminate how many local optima there can be.
Perhaps that might be an area that we might want to collaborate, because I'm active in this area. So I will send you a couple of links of recent papers so we can take it offline and discuss a little bit more.
Yeah, that sounds great. Thank you.
Great. Thanks again for your talk.
Yeah, thanks. We do have more questions from our audience. Eric asked, for the four-way stop, where four vehicles arrive at the same time, wouldn't the graphic-based resolution with 4 segments resulting in each vehicle get into C1, C2, C3, C4 accordingly, and then got stuck? How to address that?
Nice catch. Yes, I didn't mention there's a tie-breaking mechanism in the algorithm. That is, we know we let all the vehicle communicate, send their the VIN number. And that is a unique number, and then we break the tie according to that number. So yes, that's still a limitation of this algorithm, because then all the vehicles need to agree on the same consensus mechanism. Otherwise, they will still get stuck, and due to the symmetry.
Wow, that's a smart solution actually to solve that. Yeah, cool. So our audience, Dark, also asked, how do you reinforce collision avoidance constraints? How about shape and size of different vehicles? Do you take circular approximation for the shape?
Yeah, that's a very good question. I'm not sure if I included somewhere here. We actually just use a bounding box for each vehicle, and that is encoded in this collision avoidance constraint. And then we just directly convexify this collision avoidance constraint. Yeah, if you want to know more details, maybe you can refer to this paper. And also we have some other paper I didn't list, but I can share in the chat.
Awesome, that would be really helpful. Yeah, with that, we can go to our social break session. And I remember, Changliu, you mentioned you have several questions for Dr. Zhao Ding. So would you like to ask that during this break session? This is a very free session, so we can do the QA, and we can also allow some audience to introduce their work or themselves. Yeah, so maybe we start with some questions from Changliu.
Yeah, so actually I'm curious for that 6 scenario intersection. It seems that the number of scenarios highly depend on the metric you define to measure the similarity between scenarios. So is there any fundamental fundamental guidance on how to design those kind of metric and what might be the correct number of clusters?
Looks like Dr. Ding maybe offline currently. We can go back to those questions later. Yeah, maybe we can also discuss that offline. Thank you. Yeah. Any other questions from our audience, or just introduce yourself? This is for the virtual social break session. Yeah.
I have a question for Dr. Changliu. So we know that in real world, human drivers have diverse driving behaviors, which means that each driver has her unique driving behavior. And besides, each driver has stochastic driving behavior as well. So in your approach, have you ever considered both uniqueness and stochasticity of that particular driver for any prediction or learning approach?
I think our approach is to address the uniqueness by exploring the local overfitting of our model to the specific driver. But in terms of stochasticity, yeah, that's a very good question. We haven't explicitly account for that because our underlying assumption is that the driver or the human will not change dramatically locally. There's some smoothness of their behavior, so then we can apply the adaptive control approach to track it. If there's sudden change, our approach probably cannot deal with, then that will be an important research question for the future.
Okay, thank you.
Any other questions from our audience?
I guess this is a good timing for the audience to perhaps ask a question or introduce herself or himself. We have 3 more minutes that we can sort of call the social interaction, make it a little bit more interactive. Don't be shy.
Yes. Cool. So I do have more question around this model adaptation method, Changliu. So how does that generalize to the cyclist and pedestrian?
I think as long as we have a predefined offline model, no matter it's for vehicles or pedestrians or cyclists, then we can use the real-time measurement to adapt it. So it's kind of a model agnostic method.
Wow, that's really awesome. Yeah. Another question. So you mentioned that we can use the data that from the decision boundary to actually augment the data. So during the application of this method, how do we actually effectively identify the data that near the decision boundary and send to the labeler to label them?
That's also a great question. So yes, for simple models, it's easy to do some gradient descent to find the decision boundary. But for neural network models, it's very challenging. And we've developed a toolbox called neuroverification.jl, which turned this boundary finding problem into some adversarial attack problem that can be solved using formal verification. The main idea is we just try to find the minimum radius to existing minimum attack to an existing data point such that the output change. And this is an adversarial attack problem. And then we can use the state-of-the-art verification approach to solve it.
Oh, that's really, really cool. I think that can also be used for a lot of the industry as well. Yeah, really,
but
really
there's
cool.
a caveat, it's still very computationally expensive to do that. So in the future, if we can make it fast, then it will have more wider application.
Yeah, really cool. I think computational cost is something that we can solve offline if it's just a data problem. Yeah, that's really, really cool. Thank you so much. So with that said, it's time for our next talk. And Andreas will be the moderator for the second session for this workshop.
Great. Thank you so much, Jan. And thank you all the speakers in the first session. Great talks, a great discussion. I hope that the audience have enjoyed all the discussion so far. So we'll continue the workshop with Professor Yiheng Feng. We have all the bios on the website, so I'm not gonna go through the bios. I'm just take advantage of the time on the technical work. But I just want to mention that Yiheng is assistant professor at Purdue University. Actually, he recently joined Purdue University. He used to be assistant research scientist at the University of Michigan, where he also graduated with a PhD. Yiheng, the floor is yours.
Thank you, Andreas. Let me share my screen. Okay. All right. Can you see it?
Absolutely clear.
Okay, great. Thank you. Thank you for the introduction, and also it's great to have this opportunity to present our recent work. So the first session of this workshop is very informative. I hear a lot of topics from different perspectives of the CAV system, right? From the mobility system, from the mobility services to individual vehicle motion planning, and also the autonomous intersection management by Professor Liu. So today I'm going to provide another perspective in this for the controlling the CAV systems from a transportation perspective, from the traffic control and the traffic management. So what I'm going to talk about today is a recent work regarding a cooperative driving framework for urban arterials in mixed traffic conditions. So basically, there are three keywords here. You can see one is cooperative driving. That means the cooperation between vehicles and the cooperation between vehicles and the infrastructure. And then we talk about the urban arterials. It's more than a single vehicle or single intersection. It's more like even we talk about multiple intersections in the network. And finally, it's about mixed traffic conditioning, right? As some of the previous speakers also focused on this. We have CVs, we have regular vehicles, and we also have connected vehicles. So that's a mixed traffic condition. So I'll start with a little bit background about cooperative driving automation from the traffic control perspective, right? So with this new CAV technology, actually it brings two opportunities for the traffic control. One is that it provides a new data source, right? Traditionally, in the traffic control system, we rely upon the fixed location infrastructure sensors, for example, video cameras and loop detectors, which can only provide the fixed location data. But now with this connected vehicle technology, the vehicle is broadcasting proactively its trajectory. So we can enable the trajectory-based traffic control. And the second opportunity is about the CAVs, right? Previously, the human-driven vehicle are not controllable, but now for the CAVs, we can plan the vehicle trajectory. So that's about the CAV trajectory planning, which extend the urban control framework from only spatial to now spatial temporal. Okay, so the second feature is, as I briefly mentioned, that for a long period of transition time, we're dealing with this mixed traffic condition with connected autonomous vehicles, connected vehicles, and also regular vehicles. So the difference is the CAVs are both controllable and observable, and the CAVs are observable but not controllable, and then regular vehicles is neither. And finally, from a traffic control point of view, we're not only looking at individual vehicles or individual intersections, we're looking at least a corridor level or even network level, the system and operations. All right, so this slide shows a recent SAE standard for cooperative driving automation. So on the top, I think many of you are familiar with this vehicle automation level, from level 0, no automation, to level 5 fully automation. And on the left-hand side, it actually shows this levels of all the classes of cooperative driving automation. So from a transportation infrastructure point of view, it can also participate in different levels, right? From status sharing, for example, the infrastructure can provide the signal timing and phasing data, as well as the map data for the autonomous vehicles to plan their trajectories, up to this agreement seeking and also prescriptive, which means the infrastructure can also participate in this decision-making process and provide guidance or even plan detailed trajectories for all the vehicles, right? So, what I'm going to present today is about this one of this cooperative driving framework that we developed. Okay, so this is the overview of this cooperative driving framework. So it's a hierarchical control framework consisting of 3 levels. On the corridor level, we mainly want to promote the coordination between consecutive intersections, right? One of the goals for the urban traffic control is to make coordination between intersections to let the platoon of vehicles passing consecutive intersections without stop. So this is the goal of the corridor level. And then at the intersection level, so we try to optimize 2 things at the same time. One is the traffic signal timing, and the second is the arrival time of the CVs. Basically, this serves as the high-level guidance of the CV trajectory planning. And the goal of the intersection level is how to minimize the system level delay of all the vehicles. And then given the arrival time of the CV, so each CV at the vehicle level plans its own trajectories, right, following the infrastructure guidance. And the goal of the trajectory planning at the vehicle level, because you can consider the travel time is determined by the intersection controller. So their main goal is to minimize the fuel consumption and emissions. And of course, we consider also the cooperation between different CVs. For example, if the CVs stick together, they can form a CCC platoon. And we have different platooning behaviors. All right, so this is the main framework of this cooperative driving. So the next, I will talk about each levels of models one by one. So we start from the vehicle level model. So in vehicle level model, we mainly have 3 models. One is the CCC model, right, which basically describes the behaviors of the following vehicles in a CV platoon. Okay, and the second model is the ACC model. So we chose the intelligent driving model as the ACC model. So the ACC model serves 2 purposes. The first purpose is that when a CV is following a regular vehicle or a connected vehicle, I mean, the human-driven vehicle, then it will apply the ACC model. And the second is ACC model is served as the safeguard for the trajectory, eco-trajectory planning model, because of the uncertainties and also disruptions in the traffic flow, right? For example, if there is a regular vehicle suddenly cutting in front of the CV and its eco-trajectory, the eco-trajectory planning model may not realize it. So the ACC model will kick in to choose a more conservative acceleration to execute. Okay, and finally, this is the eco-trajectory planning model. This is mainly applied to the leading vehicle of the CV platoon, which plans an eco trajectory to minimize the fuel consumption. So this is one of the model we developed previously, utilizing by applying a trigonometric family of the speed profile to do the eco-trajectory planning. Okay, so in order to integrate all the different models, so we designed the station transition diagram on the right. So we defined 5 states from the vehicle entering the communication range of the intersection until it leaves the intersection area. So it will be in one of the following states, and based on different traffic conditions, based on different positions in the plateau, they will transfer from one state to another. Okay. So then we come to the intersection level models, right? So as I mentioned, the main objective of the intersection model is to minimize the total delay of all the vehicles. So then the first question is how to estimate the delay. So what we have done is to develop a shockwave profile-based model utilizing the shockwave theory to track the speed of different shockwaves to predict, for example, what is the current queue length, what is the maximum queue length, and giving the traffic signal timing when the queue start to discharge, and how long does it need for the queue to discharge. For example, here we calculate a green window in which this is basically the feasible time interval for the CVs to pass intersection. This is the time when all the queues have been discharged, right? And of course, when the penetration rate of the CVs are very low and we do not have enough data to describe or to estimate the shockwave speed, then we also combined with this traditional input and output model, basically collecting data from the loop detectors on the entries of the link and also the exit of the link to record the arrival and departure profile of the vehicles, and then applying a car-flowing model in between to estimate the queuing dynamics. Okay, so with the queuing dynamics, we can estimate the delay, and then we model this integrated optimization problem as a mixed integer linear programming problem. So the main objective is to minimize the delay, and also there's a secondary objective is to minimize the deviation of the offset, which I will introduce next in the corridor level model. And the primary decision variables are, one is the green duration of each traffic signal phase, and we assume that the traffic signals follow this during barrier structure, which is a common structure in North America. And the second set of primary decision variable is the time of arrival of each CV at the intersection. Okay, so there are three main sets of constraints. One is the signal constraints, mainly regulates the signal timing to follow the during structure. And then time of arrival constraints, which mainly regulates the arrival time of the CVs in terms of, for example, you need to follow the governing rules of the Newtonian rules, and also to make sure that assign the time of arrival fall into this green window we estimated, and also to limit the speed and have a speed limit, of course. And then finally, the third set of constraint is the CCTA platooning constraints, which regulates the platooning behaviors when two platoons should merge and when a platoon should split, based on the queuing dynamics and also the signal timing. So with the combination of the vehicle level model and the intersection level model, we can actually model the driving behaviors, right? Here, the two videos shows two different behaviors. One is the CCC string split. So let me forward a little bit. So you can see there are, this is the only demonstration case, right? So there are 5 vehicle platoon is approaching the intersection, and based on the arrival time assigned by the infrastructure, by the traffic signal, the first 2 vehicles decide to pass the intersection, and they speed up a little bit to catch up the assigned arrival time. And the rest three vehicles decide to, because their assigned route time is for the next cycle, so they start to decelerate long before the signals become red, right? So that to plan a trajectory that can have the best fuel consumption. Okay, so then the next behavior is we call the coordinated launch. So this is under 100% penetration rate where all the vehicles are CVs. And you can see when the signal turns to green, the entire platoon starts to launch at the same time as the entire platoon. So it's very different from the traditional vehicles that launch one by one. So in this case, we can greatly increase the capacity of intersection and reduce the delay. Right, so this is the combination of the vehicle level and the intersection level models. But from the second vehicle, you can still see, right, at the red signal, there's a large platoon is stopping at the traffic signal waiting for the green light. So then the corridor model, the corridor level, we try to solve this problem. So the objective of the corridor level model is to optimize the offset between the intersections, giving the green split in order to promote the progression of those platoons. Right, so we consider a two-way coordination, and we try to minimize the delay from both the primary and the secondary platoons. So the primary platoons are the vehicles that are coming from the previous the upstream section, and the secondary platoons are the vehicles that are coming from a side street. So right, so intuitively we need to adjust the signal timing of the downstream street to minimize the delay of these two platoons. Right, so what we do is we formulate it as a linear programming problem, and using offset, of course, is the decision variable. So in order to, again, analyze the delay at the corridor level, we developed this link performance function. In this case, by analyzing different signal timing, different platoon size, and different platoon speed, we divided the link performance function into 6 different cases. So basically, the horizontal axis is the offset, and the vertical axis is the volume, and the area is the delay of this particular link performance function. And based on the analysis, we summarized the link performance functions into 2 categories. The first category on the top right is when the traffic is under undersaturated traffic condition, where the green time is enough to serve the entire platoon. So in this case, when we optimize this offset, there's this LPF4, right? This section, we can minimize the delay to 0. Okay, on the other hand, on the bottom right figure, what we show is oversaturated traffic condition where the green time is not enough to accommodate the entire platoon. So in this case, no matter how we optimize the offset, there still be some delay. But still, you can see we can find the optimal, global optimal, because this is convex. And further, we actually use linear functions to approximate those quadratic PPCs. So that's why we make it a linear programming problem to basically improve the computation efficiency. Okay. Then this is this control flow chart. So we apply different control resolutions to the different layers, right? So it's more like a rolling horizon scheme that for the trajectory planning, vehicle level, we plan the trajectory every 0.1 second. And for the intersection level, we optimize the traffic signals and arrival time of the vehicles every 3 seconds. And then on the corridor level, we optimize the offset every cycle. Okay, so this is mainly the control framework. And then we implement this to a 6 intersection corridor in Ann Arbor, modeled in Visten, which is a microscopic traffic simulator, and we collect the data from the real world to calibrate the model. And we use a coordinated actuated control as the baseline for comparison, which is the state of practice in the real world. And we consider two series of experiments, CAV plus CAV and CAV plus RV. And this is the performance measures in terms of the mobility, right? So you can see in both cases with the increase of the CAV penetration rates, the total delay decreases and also the average speed of all the vehicles increases. This is a delay from the entire network. It's not from a single vehicle or single intersection. And similarly, for the INH performance, right, we apply the EPA's MOVES model to measure the INH efficiency, and both the CO2 emission and also the total INH consumption is reduced with the increase of the penetration rate of the CAVs. Okay, so one of the reasons why it is because with the higher penetration rate of CAVs, it is more easy to form the CCTA platoons, right? As I showed in the second video, that when the platoon is formed, the coordinated launch and also the reduced headway between the vehicles can reduce delay and improve the capacity. And finally, what we did is a analysis on the dynamic offset optimization. As I mentioned, we try to optimize the offset of the traffic signal timing every cycle, which is different from the current practice. Usually the offset is fixed. However, we have different demand levels, right? Cycle by cycle demand fluctuation, and also with different platoon size, with different platoon speed. So in order to accommodate those local variations, so we try to optimize. That's the motivation why we want to optimize the offset dynamically. And this figure shows the additional improvement with this offset optimization. So you can see from both the total delay, number of stops, and the fuel consumption. So by optimizing the offset, we can have a few percentage of additional benefits. Okay, and when the volume fluctuation is increased from like 5% to 10%, you can see also the benefit is also increasing. That's also kind of confirms why we're doing this. Okay, so to finally, I talk a little bit about future research. One is that currently we only model the longitudinal behavior, mainly the car following in this framework. So we need to add the lateral behaviors, for example, the lane changing behavior into this framework. And the second thing we can extend is if we look up, right? If we really look at the network level, then we have another important issue we need to deal with. That is the road choice, or sometimes we call traffic assignment in the transportation network, giving a pair, a set of origin and destinations, how to assign routes to these vehicles. Again, in a mixed traffic condition, we can assign the routes for the CVs, but we cannot assign the routes with regular vehicles. And how to integrate this route choice problem with the lower levels of those problems. I think it's a very underexplored area. And the third one, if we look down, right? So it's how to integrate with the real connected and autonomous vehicle motion planning problem. So as you can see, our trajectory planning model is kind of simplified. As Professor Peng presented in his presentation, there's a lot of uncertainties, lags, and delays in the motion planning and execution, and then how to integrate these into the traffic control framework. So if we integrate all of them, then it kind of an end-to-end controlling model for the CAV system in the transportation network. Okay, finally, this acknowledgement for our sponsors. And so today I mainly talk about the concepts and ideas of our model. If you are interested in model details, you can refer to those two papers. And I also want to thank all the co-authors in our two papers. I think that's all I want to present, and thank you, and I welcome any questions.
Great, thank you so much, Yiheng. Let us virtually upload our speaker. It was a very interesting presentation. It seems that we have already one question from Ziran for you, Yiheng. You can read it, or I can read it for you.
Yeah, let me check the.
Ziran is asking whether the proposed framework works for fixed timing traffic signals or it works for actuated traffic signals.
Oh, okay. So in this case, we actually integrated this trajectory planning with adaptive signal control. So we optimized the offset and also the brain split of the traffic signals. But of course, if we fix, actually, I should separate this, right? If we have a fixed traffic signal, it can work with any without modification, because with fixed traffic signals, the traffic signal is determined. We know the deterministic information of traffic signals. It's more like in our case, although the traffic signal is optimized adaptively, but from the vehicle level, this information is passed to the vehicle level. From the vehicle side, it is deterministic. However, for the actuated traffic signal control, this is there's another problem we need to address, is how to predict the signal timing. I know there's some work out there how to predict signal timing. Then there's uncertainties in the trajectory planning again, how to address this uncertainty from the traffic signals.
And that actually was the second part of the question from Ziran. I think Ziran, Yiheng answered the question for you. Okay.
All right.
Yeah, and also he has another follow-up question, which is also my question. This is something that I was about to ask. How about the mixed traffic scenario? Do you consider uncertainty of the human behaviors or of legacy vehicles?
Yes, in some sort of, we consider that. So as I mentioned in this slide, right, when I talk about the ACC model, one of the function of the ACC model is to dealing with uncertainties of human driven vehicle. It's like a safeguard. When the human vehicle did some unexpected behaviors, this ACC model can kick in and replace the eco-trajectory planning model to make sure that the safety gap can be maintained.
I see. Any other questions for Yiheng from the audience?
Thank you so much, Yiheng, for the nice talk. I have one question regarding the connectivity that you used here. Did you observe any difference if we compare the connectivity signal coming from infrastructure versus connected signal from the vehicles? So what are the pros and cons when applying these frameworks by using those two different sources of connectivity information?
That's actually a very good question. So in this work, we are mainly consider the connectivity from the infrastructure side. So we are mostly formulated a centralized control problem. The infrastructure assigns the travel time of all the vehicles. But if we are talking about the connectivity from the vehicle side, then we probably can model it as a distributed control problem, right? Then the connect vehicles, those connect vehicles need to make consensus, some forms of consensus it's more like what Professor Liu just presented at this autonomous vehicle intersection management, right? This consensus is made from the vehicle side.
Yeah. In the real application side, how do we actually use effectively from the both side of connectivity based on your opinion?
So from the application, from the implementation point of view, I can speak from the infrastructure side. I think SAE is also developing a message, a new message called the roadside safety message, which would contain some of those guidance from the infrastructure, more additional information and guidance from the infrastructure. But from the vehicle point of view, I'm not sure whether there exists a information like a message that contains those information. I mean, from the official standard point of view.
Got it. Thank you so much. Super helpful.
Very nice. Of course, we'll have a chance to ask more questions to Yiheng at the end of the workshop. In the meantime, let's thank our speaker again, virtually thank our speaker again.
Thank you.
Thank you for the great talk. Excuse me. So now we'll proceed to our next speaker, who is Dr. Ziran Wang from Toyota Motors North America R&D. As I said previously, we have all the bios of our speakers on the website, so you can find the details information. But just I want to mention that Dr. Ziran is a principal researcher at Toyota Motor North America R&D, and he currently co-leads the digital twin projects with the aim to build an AI-based data-driven vehicle-to-cloud framework. So with this, Ziran, the floor is yours.
Thank you very much, Andreas. Can you see my screen?
Absolutely.
Thank you a lot. And it's really my honor to present our work here in this workshop. And this work I'm going to present is a collaboration between Toyota Infotech Labs and UC Riverside. And I'll first talk a little bit about the background of this whole project, besides specifically about copyright merging. We talk about digital twin a lot, especially I'm leading this project from Toyota's side. But what do we mean when we say digital twin? So we propose this digital twin framework for not just vehicle, but also for traffic, for driver, which is more like a AI-based data-driven vehicle-to-cloud framework to benefit our society, to improve the safety, mobility, environmental sustainability of our whole transportation systems. So you can see there are two different spaces of this digital twin framework. In the physical space, we have road network, which is the surrounding information, traffic signals, as Dr. Feng just mentioned, and intersection geometry and ramp geometry, things like that. We also have our vehicles, where those vehicles will be connected vehicles. Some of them will be connected automated vehicles. Some of them will just be human-driven connected vehicles. But all of those vehicles, they have this kind of capability to communicate to the cloud. So they can upload their data to the cloud. They can receive guidance from the cloud. So the physical space will, in charge of these two processes, sampling data from different sensors, like from traffic signals for signal phase and timing, and from perception sensors, localization sensors from their vehicles, and then actuate the command, which is the last step of this. The commands comes from the digital space. So the digital space, we build that on the cloud server, but we can also build that on the edge server or any virtual server, and that is in charge of all of those 5 functionalities to store different data, not just the current data, but also historical data, to simulate different vehicles' behaviors, drivers' behaviors, build models, conduct machine learning, and then predict future behaviors of the vehicles, of the traffic signs, of traffic signals, and of other drivers. So as I said, it's for traffic and driver. For traffic, we have some certain microservices of this digital twin. For driver, we also have some microservices like to predict other drivers' behaviors based on their classification. And in this talk, I will mainly focus on the second pillar, which is the vehicle digital twin. The basic idea is to create this virtual copy of different connected vehicles by receiving their data, build their models, and then use our algorithm to conduct this kind of cooperative decision making or cooperative motion planning, as well as cooperative motion control, so that those vehicles, they can collaborate with each other, not just by leveraging their real-time communication, real-time information, but also to leverage in their historical information. So that's why I put this kind of storage sign right here. And those all those data that are stored on the cloud will be beneficial to the real-time decision-making and motion control. And we can dive into the specific scenario that I'm going to talk about in this talk, which is ramp merging. And I believe many of us have experienced some difficulties in the ramp merging scenario sometime. And let me see whether this video can be played. If you see the video on the left, it was actually taken by me 2 years ago on my way to work here in the Silicon Valley, where you can see all those vehicles are waiting to merge into the mainline traffic of this Central Expressway in Santa Clara. And the reason for this congestion is really not ramp metering, because there was no ramp metering at the end of the ramp. But because of the ramp length is just too short, and the mainline vehicles, they are just traveling too fast. And those mainline vehicles, they don't have, they have the right of way, so they don't necessarily need to show courtesy to the merging vehicles. So the merging vehicles just waiting forever, trying to find a spot to accelerate to merging, and it's really dangerous because the ramp is very short after you turn right. And on the right, this video, I would say it's kind of like the nightmare scenario, as everyone can imagine, when you are sandwiched by two giant tracks, which we will see later. So, the vehicles accelerate, go into the ramp, go into the main line, but there are just two giant trucks, and it's hard for you to just merge in. And those giant trucks, they have the right of the way because they're on the main line. So all those different scenarios really introduced me, the intention to think about, what if we have connectivity among those vehicles? How does that help? Can they collectively work with each other so those mainline vehicles can show, in some degree, some courtesy to the ramp drivers, so that ramp drivers will feel safe and to conduct this ramp merging scenario? Then this is a concept of our idea, and I will come back to this figure later. So basically, we have different vehicles trying to merge, those mainline vehicles on the rightmost lane and the ramp vehicles on the ramp. And the key concept is we use this kind of digital twin technology, or it's virtual vehicle technology, to kind of project those vehicles that are the leading vehicles of the others in their own lane. For instance, for this vehicle 4, ramp vehicle 4, we project this vehicle 3 into this lane, and we consider this as the digital twin per se of vehicle 3. And this digital twin of vehicle 3 will have the same longitudinal speed, longitudinal position, longitudinal acceleration of the vehicle 3. So what the vehicle 4 needs to do is just to follow this virtual vehicle, this digital twin of vehicle 3, and then adjust its longitudinal speed and position ahead of time. So it's more like a carpooling scenario instead of a ramp merging scenario. So at the time that those vehicles, they're actually at the conflict zone, those vehicles can safely and smoothly merge without any collision, without any late decision of speed changes. And I will come back to this figure later. So next, I will talk about the system design of this work. And I know the focus of this talk is about field implementation, but I will first talk about the theoretical background, the backbone of this field implementation. This is the framework again of the digital twin framework of this ramp merging scenario. So we built again two world or two spaces. One is physical world, one is digital world. In the physical world, we have different vehicles. The Eagle vehicle and other vehicles, they are all connected vehicles for this scenario. And I will talk about mixed traffic scenario in the later slides. And those connected vehicles, they have localization sensors to get their real-time position. They have this kind of human-machine interface to provide guidance to the driver. And the reason that we don't do autonomous driving implementation is because one is our vehicles at UC Riverside doesn't have the automated capability. And the second thing is actually more important because the legal issue. It's really hard for us to conduct any kind of autonomous driving testing on the public road in some organizations like universities. So we use this kind of ADAS as a substitute for autonomous driving, but still to provide guidance to different drivers to follow the speed calculated by our motion planning and control algorithms. On the digital world, and you will see we built everything in this cloud server. We have motion planning and control algorithm, which I will introduce later. And the map matching is actually upstream of that. And it gives you a specific location on the lane based on the raw GPS data that is received from the GNSS. And we have this driver digital twins, which is not a focus of this talk, but I will elaborate a little bit at the end of this talk, which is trying to learn different drivers' behaviors in terms of following this guidance, so we can predict in some degree the uncertainties of different drivers, and then to compensate for that kind of uncertainty ahead of time. And then we visualize different digital twin vehicles and then conduct some performance evaluation. So the first part of this cooperative motion planning and control is motion planning, and which I will consider that as just a scheduling problem. When we are talking about ramp merging, it's really can be split into this kind of these four kinds of scenarios. One vehicle tries to merge into the main line, and the main line, those two vehicles either sandwich this vehicle, so this vehicle merge in between those two vehicles, or merge behind those two vehicles, or merge in front of those two vehicles, or the main line is empty, so the main line vehicle, the ramp vehicle just conduct a lane change to the main line. And since we have a lot of details of this kind of scheduling problem in our paper, so I won't dive into this pseudo code per se, but basically we want to schedule different merging vehicles based on their current speeds, especially their longitudinal speeds, as well as their distance to the merging point. And the merging point is at the end of this merging lane, as well as their distance to the interacting zone. So interacting zone happens actually earlier than that. That is the region that allows different vehicles to start engage with each other, to kind of handshake with each other, and to send their information, their speed, their position, their acceleration to each other through our cloud server. And once that's identified, and as I said, I'll come back to this figure, say if this vehicle is assigned with a sequence of 1 to merge, this is 2, 3, 4, 5, 6, then based on the lane of those different vehicles is on, we either directly apply this cooperative motion control algorithm for this vehicle 5 to just follow the preceding vehicle 4, which is on its own lane, or like vehicle 4 or vehicle 6, we project their leading vehicles from the other lane as this kind of digital twin. So those vehicles can still follow their preceding vehicles based on the motion control algorithm. So with that, this virtual vehicle sequencing method actually transforms the ramp merging scenario into a virtual car following scenario. And we have a lot of differentiations between this kind of virtual car following with real car following, like adaptive cruise control or a cooperative adaptive cruise control. So I will talk about those constraints in this ramp merging car following later. But basically, this is the idea. We convert that into vehicle digital twins, and then use our motion control algorithm, which is the car following algorithm, to be applied to this kind of ramp merging. And specifically, we propose this consensus algorithm, which is interesting because Dr. Feng and Dr. Liu just talked about the consensus among different vehicles. Here, the consensus means that we want the eagle vehicle or the following vehicle reach the consensus with their leading vehicles in terms of their speed, their position. And if you see right here in the consensus algorithm, we actually have a position consensus term where we converge the longitudinal position of my eagle vehicle I and the longitudinal position of the leading vehicle J, and we consider this time delay. There is a time delay of communication to the constant value based on the length of my vehicle, the front of my vehicle, the length of the back of this leading vehicle, because the position comes from the GPS sensor, and the sensor may be equipped with on the vehicle, in the center of the vehicle, or maybe the back, or maybe a little bit in the front. So we also want to consider that to be, you know, accurate to converge different positions of this vehicle, of these two vehicles. And then this term is based on their speed, the speed, especially the leading vehicle speed, and we assign this time gap plus this time delay. And we actually assign this BI as well as the braking factor, because we want to also gauge the ego vehicle's braking capability. Because if we are talking about this is Toyota Camry, or maybe Toyota Supra, their braking capability will be definitely different from a heavy-duty truck or a bus. So we want to also consider their braking capability to set their car falling position or car falling distance. And the velocity consensus is much more straightforward. We just converge the ego vehicle speed to the leading vehicle speed, considering the time delay. And this is the block diagram. So we have this feedback controller, which is right here. We also introduce a feed-forward controller, which will calculate kind of the optimal value of this damping gain here, because this damping gain of this feed-forward feedback control is very important. It decides a lot of capabilities of this algorithm. So we also want to kind of propose this feed-forward controller based on the initial speed error and initial position error of these two vehicles, and then calculate the damping gain so that this algorithm can perform as good as we want. A little bit more details about this feed-forward controller, so this part. So we have different constraints. So this is different from a traditional car falling scenario of those vehicles on the same lane, because we want to, of course, guarantee safety, and this is for sure for different kinds of car falling. But the major difference of the car falling on ramp merging is because, you know, those vehicles on different lanes, their initial speed error might be very large, because maybe the ramp vehicles just start from a rest signal. They just turn right after the rest signal, so their speed accelerates from 0 to 45 miles per hour, 60 miles per hour. But for the mainline vehicles, they have been traveling very fast already. Maybe their speed is already 70 or 80 miles per hour. So their initial speed error is pretty huge, and their initial position error can be huge as well. So we want to make sure that their safety is always guaranteed by evaluating their headway overshoot during this whole process. And we also want to guarantee the efficiency of this ramp merging by evaluating the convergence time of this algorithm, meaning that we want those two speed of these two vehicles, the leading vehicles and the following vehicles, to converge as soon as possible. Because otherwise, if they don't converge before they see each other, then this cooperative ramp merging doesn't make sense. And we also want to evaluate the comfort by maximizing acceleration, or by calculating the maximum acceleration and deceleration and maximum jerk of this whole system, this whole merging process. So we can choose the damping gain gamma to make this these two parameters as low as we want to guarantee the comfort of this car falling of ramp merging. So next, I will dive into a little bit about simulation. We do simulation, of course, before the actual field implementation, just to validate our algorithm and to see whether that works. This is the game engine simulation that we conducted in the Unity game engine, where, as you can see from the left figure, those mainline vehicles 1, 2, 3, 4, 5, they decelerate ahead of time to create this kind of space for this ramp vehicle, because this vehicle on the mainline is already assigned a number of 3 after merging. So it identifies, okay, this is my preceding vehicle, and this preceding vehicle's digital twin has already been placed there before they actually merge. So at the time that they actually see each other, they have the line of the sight. At the end of this ramp, this gap is already created for this vehicle. So all this ramp vehicle needs to do is just to, change the lane to the left and then merge into the main line. And you can see from this right figure as well. At the beginning, those 6 vehicles, they are traveling in a vehicle stream on the main line. And then once the vehicle is identified, okay, this is vehicle 3, the ramp vehicle is vehicle 2, and that vehicle is vehicle 1. then the gap will be created on the main line. So this vehicle, at the time that they actually see each other, this vehicle can just smoothly merge into the main line without any late decision, without any potential collision. And this is the outcome of the simulation, where you can see this is the speed trajectories of the ramp vehicle, and those are speed trajectories of the mainline vehicles. The mainline vehicles, starting from vehicle 2 to vehicle 6, they decelerate just a little bit to create that gap based on the algorithm that we propose, so that at the time that those vehicles, they are actually around this merging zone, they don't need to change their speed anymore because their speed and their position has already been adjusted ahead of time. Compared to these two scenarios, where those scenarios, there is no information change among any kind of vehicles. So the drivers will just drive in a simulator without being notified of any other vehicles that are emerging from other lanes. So you can see this coaches driver, it actually, this driver attached to the end of the mainline string. It's because this driver was too cautious. He or she was hesitating to merge into mainline. So he just, go to follow the last vehicle on the mainline. Compared to this one, this driver was a little bit more aggressive. The driver wants to merge into mainline, but really hesitates to find a sweet spot. So you can see the speed trajectories accelerate, decelerate, accelerate, decelerate, which introduce a lot of safety risk for those mainline vehicles. You can see those perturbations caused by this ramp vehicle, and it's also not efficient. If you compare our travel time of the cooperative ramp merging scenario with other baseline scenario, you can see we can, reduce travel time, and we can also save energy for sure because it's much more smoother, those speed trajectories compared to the coaches driver case or aggressive driver case, or even normal driver case. So this is about simulation. I will touch about the field implementation. Here we have this kind of 3 vehicle merging scenario in the field implementation, which is a little bit more simplified than the simulation, where we have different hardware equipped on the vehicle, which I just introduced earlier, and they will be connecting to the cloud to talk with each other and exchange their information with each other. And specifically, what I want to talk about is this user interface. And as I said earlier, due to the difficulties of testing this in the public road for autonomous vehicles, so instead we developed this kind of user interface as a feature of an advanced driver assistance system to give the guidance to different drivers. And the guidance is actually works as right here. There are 2 numbers are shown to the driver. The left number is the current speed of the vehicle. The target speed, the right number, is calculated by the motion planning control algorithm that I just introduced earlier. So what the driver needs to do is to follow this speed to kind of perform as autonomous driving, right? Perform as a robot driver to follow the speed guidance and then conduct this kind of cooperative ramp merging scenarios with other vehicles. And as you can see from the right, this is the passenger UI that we introduced. So the passenger sitting on the back seat can also see this whole bird eye view of the ramp vehicles to gauge, okay, whether I'm in a good spot, whether I'm still lagging behind, things like that. But the driver needs to focus on the driver UI, and that's it. Just trying to match these 2 numbers, which I'll introduce in the video right here. So this was done in the real world in Riverside. So you can see all these other vehicles, they are still traveling. There are 2 mainline vehicles, 1 ramp vehicles, and the mainline vehicles and ramp vehicles, they constantly talk to the cloud about their speed, about their position. And in this time step, the ramp merging scenario starts to kick in, the cooperative ramp merging scenario, where this second mainline vehicles notify, okay, I'm assigned as a slot of 3. So it's better for me to find my leading vehicle, which is leading vehicle 2 on the ramp. And then I will start to decelerate to create this gap for this ramp vehicle to merge in. So you can see at the time that they actually have the line of sight, the ramp vehicle can safely and smoothly merge in without making any late decisions. Am I going to merge? Am I going to attach to the end? Am I going to, going to the front of the vehicle, things like that. And you can see this is the digital twin view of those 3 vehicles on the cloud in real time. And their position is a little bit bumpy because it's caused by the error of the GPS sensors. And you will get a flavor of how the drivers are following the guidance in this graph, in this figure, as well as these 2 videos. So this is the view of the following vehicles on the main line, and this is view of the RAM vehicle. And you can see that we introduced some kind of trigger methodologies to generate this kind of RAM merging scenario, because otherwise if this RAM vehicle accelerates ahead of time, then there's no RAM merging at all. This vehicle can just merge into the front of the vehicle. So but during the time of this merging, you can see this second vehicle on the main line decelerate during that process, and the driver tries his best to follow this speed guidance. You can see there's very minimal error between these 2 numbers because our drivers, they perform pretty well. But for any new drivers who just try the system, this is actually not that difficult as you can imagine, because the drivers have the algorithm already considers some of the uncertainties of this driver's performance, and also to consider the capabilities of acceleration and deceleration at each time step. So the target speed won't be that far away from their current speed. And on the other hand, those other drivers at the time that they actually merge, they can see other drivers. So they can, once they have the line of sight of each other, they can just forget about this user interface. They can just conduct their lane change by themselves because the gap is already there. It's pretty straightforward for those RAM vehicles to merge in without any late decisions. So that's the concept. It's just a proof of concept of this cooperative RAM merging. I know this is kind of simplified, but once we have more vehicles following that, it will be pretty similar to this. Those other vehicles will behave as similar to the simulation, and they will create this gap for the RAM vehicles merging. With respect to the results, it's kind of similar to what I showed earlier in the game engine simulation, where this RAM vehicle accelerates, just trying to catch up with those 2 mainline vehicles. And then at the time that they actually see each other, the speed is already very constant, and they will just proceed with constant speed to the merging point without any last minute speed changes. And you can see these 2 mainline vehicles, they decelerate just a little bit to create this gap for the vehicles, especially the second vehicle, mainline vehicles, to allow the RAM vehicle to merge into that gap. And then after they see each other, their speed already reached consensus, so they don't need to do any last minute decision. And interesting result is regarding the communication. Here, I didn't talk about that, is that we use 4G LTE communication among different vehicles. And actually, vehicles talk to the cloud and talk to our vehicles. And we use that Wi-Fi dongle to allow those information to be transmitted across different vehicles. And as you can see from this end-to-end delay, so it's not just communication delay, we also consider cloud computing process time on our cloud server, which was built by UCR. It's a private server. And you can see the communication delay is actually not that bad. The average delay is around 80 milliseconds end-to-end from one vehicle, send that information to another vehicle, receive that information. And that information is already processed by the proposed motion plan and control algorithm on the cloud. Which means that this can be introduced as an assistant to the driver to some degree, but in the future, if you can decrease the cloud computing time on the cloud and also to use maybe 5G communication in the future, then this end-to-end delay will be reduced for sure. Energy consumption and pollutant emission results, we can also reduce pollutant emission in terms of different parameters and also reduce fuel consumptions by almost 7.5%. And we're running this based on multiple trips of these RAM merging scenarios, where RAM merging scenarios, their initial speed and their initial positions are also different in those different scenarios. And we can achieve this kind of positive feedbacks. And the last slide, I want to touch very high level some of the future work or actually ongoing work of this cooperative random merging. As several speakers talked about earlier, the driver uncertainty is very crucial, not just for understanding their behaviors, but also to plan the motion control of other connected and automated vehicles. Because if those CAV, they don't know other drivers' intention, they cannot predict other drivers' performance, then it's really hard for them to react in real time. What if that driver is pretty aggressive? That driver always merges into mainline at a very late stage. What if that driver is pretty cautious? He or she doesn't want to merge into mainline at all. So in that fixed traffic scenario, in the future, we have human-driven vehicles, we have CAVs. We want to build this driver digital twin on the cloud to store different drivers' performance data on the cloud. So in real time, once we see each other, we see, okay, that is the human-driven vehicles. We have our own perception sensors on my CAV to detect that driver's performance over maybe the last 10, 15 seconds. Then by using that 10, 15 seconds of data, we match that to the historic data on the cloud, and we are able to classify that driver into maybe aggressive driver, cautious driver. Then we can apply the pre-trained neural network on the cloud to be assigned to that vehicle. So, okay, once we see that driver, we follow that driver for 10, 15 seconds, we're able to predict that driver's future behaviors, maybe 5 to 10 seconds in the future, which can be very important and very helpful for our cooperative autonomous driving to, either to change a lane to the other lane, or maybe to create a gap for that vehicle, or to maybe just accelerate as we want because that vehicle is a cautious driver. The driver doesn't want to merge in at all. So we have some ongoing work on this. Please feel free to follow us for some updates. And our contacts right here. And I want to thank all my collaborators for this work. This work is actually leading by PhD student Xishun Liao from UC Riverside, and my colleagues Quinte Han, Prashant Tiwari at Toyota, as well as PhD student Peng Zhao, and my former PhD advisors, Dr. Matthew Barth and Dr. Guoyang Wu. With that, that's all about this talk. Thank you very much for listening.
Great, thank you, Ziran. Let's virtually applaud Ziran for the great talk. Very interesting approach. We are a little bit tight on the time, so I'm suggesting let's move on to the next talk, just to keep on schedule, and then at the end we'll entertain questions for all the three talks in this session. That sounds good, Ziran, for you?
Sure. Thank you, Andreas. Yeah. So
absolutely. So our last but not least speaker is Dr. Chang, for which we have this great workshop today. She worked really hard to put this together. Again, the bios of all the speakers are available in the website, but just want to mention that Dr. Chang received her PhD from the University of Michigan, and she's currently the lead, the tech lead and senior software engineer at level 5, formerly part of Lyft, but now is Woven Planet, a subsidiary of Toyota. Her current research focuses include machine learning, motion planning, and decision making. And with this, I would like to turn it to Yang, and we look forward for your presentation, Yang.
Thank you so much for the introduction. So today we are going to talk about data-driven planning for the autonomous driving. So before we get started, please allow me to introduce Level 5. Level 5, formerly part of Lyft, currently a part of Woven Planet, a subsidiary of Toyota. And the mission of Level 5 is to deploying self-driving technology to create safe mobility for everyone. And at Level 5, we combine the Silicon Valley innovation and the Japanese craftsmanship together to make the innovation and technology to happen. So today I'm mainly going to talk about the following things. Firstly, we will talk why is a data-driven self-driving system promising. Secondly, I will talk about data-driven planning system. And then we will talk about how to test this kind of system. And last but not least, how do we actually collect enough data for this type of system? And so before we dive into those details, firstly, let's take a look at autonomy 1.0, which is a traditional self-driving stack. So it concludes the several different portions of the autonomy stack. So firstly, we use sensor input to generate the perception output. For example, all the agents and the obstacles locations. And then we use those information together with map information to do the prediction for all the agents so that we generate the trajectory for each agent. And then using all those information, we do the planning. So during the planning, we can generate a trajectory for ego that can be executed by the controller. And then we do the all kinds of different testing to do to evaluate the whole system. And as we can see, actually, the amount of machine learning in the autonomy 1.0 is primarily coming from the perception and portion of the prediction. But traditionally, in the traditional planning stack and evaluation stack, we use quite limited amount of machine learning. So that gives a lot of limitation for the autonomy 1.0. So firstly, a lot of handwritten rules are used in the stack, and we know that handwritten rules are not that scalable. And also the engineering individual blocks are relatively complex. And also, whenever we want to adapt this whole system to the new ODD or to a new geography area, we need significant engineering efforts to make that happen. And also, route testing is normally expensive and also take time. So in autonomy 2.0, which is a ML first approach for self-driving, we can use more machine learning and data-driven approach into the planning stack and testing stack. By using that, we have several benefits. Firstly, the driving behavior is defined by the data rather than engineering. And also the behavior learned from human drivers can be more naturalistic. And also the testing can be done mainly offline using the ML simulation and the data-driven evaluation. The last but not least, we can easily deploy the stack to the new area and new ODD because we mainly need to collect the data from that kind of new ODD or new areas. So before we dive into the data-driven planning, let's firstly take a look at what is the traditional planning architecture. So that is several layers. So first layer is the mission planning, where it generates the global route planning information for the ego car. And then after that, that is behavior planning, where it generates the concrete waypoints for ego to follow. And it also generates all those decision makings that our previous speakers mentioned, like whether we do lane change, whether we do the unprotected turns, all those things are aligned in this layer. And then based on that information, we plan a trajectory along those waypoints for a smooth and safe trajectory that can be executed by the controller. And then controller translate that trajectory into the actuator commands such as steering, such as throttle, and braking. So essentially, the core technology used in the traditional planning works is we use all the inputs that we mentioned, like the map information, agent information, and other like driver surface and ego's current information to do the optimization used the handcrafted features, for example, the distance to the agent, the distance to the other lane boundaries, and for example, the jerk related cost, and so on. So, and also hand-tuned those weights for each term of those features to generate or to select best trajectory for eco to execute on. But the problem with that is that those kind of features are not that easy to scale. So with a data-driven planning framework, the core idea is that we are going to leverage data to help us to identify those features and also to help us to determine the weights of different features, or in general, a more generic framework that can help us to determine those things, to help us to generate a more naturalistic and safe trajectory for ego to execute on. So that actually can scale this data. So last year, the level 5 team published the paper on the performance when we train the planning stack and prediction stack with different amount of data. And we observed that when we train the data, the stack with 1,000 hours of driving data, the interventions per 1,000 miles decreases significantly, which again gave us a promise that the method that this data-driven planning method can scale this data. So there are actually many ways to how to leveraging data into the planning stack. And I will illustrate several examples. So first example is that we can use the human driving trajectory to learn where is the optimal location in the lane that ego autonomous driving vehicles should follow. For example, in this video, we can see that it's a turn, right? And also during the turns, we know that it's not that simple to just follow the center of the line during the turns. For example, if we just follow the center of the line, that will be the purple trajectory as we see here. But actually, we found that the blue trajectory is actually what most human drivers are used. And by using that kind of like the, those kind of data, we can aggregate the human trajectory where they drive on this kind of route for a lot of times, and then aggregate an optimal location for our ego autonomous driving system to follow, which can actually give us a much more naturalistic driving behavior for this kind of turns. And also, for example, if there is a bike lane in this kind of like intersection, the traffic law actually requires ego to shift to the bike lane before the turn. So by using this method, we can easily to learn that kind of behavior instead of handcrafting where we should shift to the bike lane and how to deal with all kinds of different situations in terms of different map locations. Another way to actually leveraging human driving data is we can actually learn from human drivers how do they essentially adjust their speed and acceleration to adapt to all kinds of different scenarios. So as we can see from the plot on the left, it actually shows a plot where the x-axis is the distance to the lead obstacle. This kind of obstacle can be the lead vehicle or cyclist or even pedestrians, or even just stop sign or red traffic light stop line. And then the lead velocity or lead obstacle velocity is the y-axis. And the color showing here is actually the human's speed in terms of all those kind of different scenarios. And by leveraging that information, we can actually use that into our planning stack and to adjust or to select the best trajectory that most similar to human drivers' behavior to handle all kinds of those scenarios. And as we can see from the video on the right, so in these scenarios, the other cars from the other lane, do a cutting right in front of the intersection. And we can see that even in this kind of situation, the Eagle car can handle that pretty safely and smoothly. Let's take another look at this kind of technology. So in this example, essentially Eagle need to do a lane change, and also right after the lane change, Eagle need to go to the stop because it's very close to the intersection. This is actually our route testing data from San Francisco downtown. And we can see that even in this kind of complex situation where we need to interact this, originally follow car, the new cutting car, follow car from the left lane, and also after we change the lane, interact with a new leading vehicle which is stopped, we can do that quite smoothly and safely. So there is another method to do this, which is machine learning first planning architecture. Again, there are a lot of different neural networks that can do this type of processing or this type of motion planning stack. I will just illustrate one example. So in this example, the perception input and map input were combined together to rasterize into the bird view image, where it can be fit into a neural network. And then the neural network generates the trajectories for Eagle, essentially from this machine learning model. And then we go through a safety layer, essentially to check whether this machine learning trajectories satisfy all the traffic rules and also the safety requirement. And if it satisfies that, great. We send that to the controller. If not, it will go to a fallback mode where essentially the rule-based traditional planning stack will safeguard the system to generate a safe trajectory and smooth trajectory into the controller. So by using this kind of architecture, it can utilize the advantage from the data-driven method and also have the good backup and fallback mode where we can guarantee the safety. And so we can see some examples from this kind of like the method. So essentially we can see that even just the 3.5 hours of training data, the Eagle car, which is showing as a red box in this video, can already follow the lane quite elegantly. But let's see if we actually add more data into it. If we used 1,000 hours of training data to do that, we can see that actually the trajectory become much, much more smoother. And also, let's take other more complex examples. For example, in this example, Eagle car need to essentially follow a lead vehicle to go to the red traffic light intersection. And we can see that from a small amount of training data, it actually has difficulty to interact correctly with lead vehicles. But let's see if we add more data to it. We can see that this time it can actually follow the lead vehicle quite elegantly with a very safe distance and also be able to proceed when the red traffic light turns green. And let's see another example near the intersection. So essentially, again, there's a small amount of data. It's have difficulty to actually stand still in front of this kind of intersection situation. And when we add more data to it, it becomes much more intelligent and be able to stand still, keep a standstill mode in the intersection and be able to follow the traffic to proceed when the traffic light turns green. And let's see the performance on the real world. So essentially this is testing result from our closed test track. We can see that the machine learning version of Planner can actually handle the nudging quite elegantly for those construction cones. This video is coming from ML trajectory only mode. It's all from the trajectory that from our like the drive net that we just mentioned. And this is another example where it is taken the unprotected turns. We can see that it safely yield to the other cars and then proceed. So with that, let's dive into how do we actually testing this kind of data-driven planning system so that we can ensure that it's safe enough to deploy to the real world. And so when we talk about testing for the planning system, we mainly need to see the 4 buckets. Essentially, the first bucket is about planner metrics. So we need to define metrics in terms of safety, traffic rules, comfort. And also the caveat here is that it also, the threshold or the criteria for those metrics could be different based on different scenarios. So we also need to have a big variety of scenarios. For example, the cutting scenario resulting from stop, unprotected turns, jaywalkers, all those kind of scenarios, and also it aligns from the previous talk from Professor Zhao Ding about how do we actually generate all kinds of scenarios that have a good representative of the real world driving and also be realistic enough. And with that, we also need to have a good simulation system to actually be able to test all those things offline in a safety manner and in a very effective, efficient way. And also after that, we also need to do the road testing before we deploy these things to our customers. So in terms of like the testing, I will mainly talk about simulation in this talk due to the time limit. So there are multiple ways to do the simulation for the autonomous driving cars. A first traditional method is to do the log replay. Essentially, we use the recordings from real world driving and then essentially do the log replay in the simulation environment to see how ego car with a new planner stack or with a new autonomous stack actually react to it. The issue with that method is that the agents can't react to the surroundings. So for example, in this example, the self-driving vehicle is doing the right thing, stand still there, but the agents actually collide into ego because it's not reactive to what ego is doing. So there is another approach, which is manually code the rules of the route for all the agents in the simulation. And color is belong to that category. The problem with that is that it's not easily scaled to a lot of rules. And we know that interaction between different agents can be very complex. So the method that used in level 5 is actually, we used a machine learning simulation environment where we learn the behavior from other agents directly from the raw data, which can actually significantly narrow the gap between the reality and simulation. As we can see from this example. So again, in that previous example, with this kind of machine learning method, we call that SimNet. It can actually stop in front of ego car correctly, that the agent can actually react correctly so that we don't introduce too many false positives in the simulation testing environment. So the idea for this is quite simple actually. So the model is try to minimize the predicted trajectory for the agents versus the ground truth of the trajectory from the agent from the recording to minimize that error. And so let's take a look at more examples of the SimNet results. So the first example is where we can see that the other agents can actually do the right turn in front of red traffic light correctly, and also the cars around ego in terms of where they go straight and have the red traffic light, they correctly stand still there. And the second example is essentially where ego is, following the traffic, and also all the other agents is also following the traffic flow quite smartly. And also we can see that on the other box on the right side, actually they all stand still there because they are originally parked car there, and we correctly predicted the kind of a parking behavior from the other parked car as well. And let's take a look at the other example. In this example, essentially it's a complex intersection scenario. We can see that even the essentially the unprotected turn behavior from the other agent and even U-turn can be predicted quite correctly. So let's take a look at some of the quantitative results from this kind of like the simulation. So essentially we can see that in this plot, the x-axis is a prediction horizon for all the agents. And the y-axis is the error at each timestamp for the different training sizes. Essentially, we can see that by increasing the amount of data that's sent into this framework, we can actually significantly reduce the error at timestamp for the agent prediction. And also we can see that the longer the horizon is, the larger the effect is. So another question we might encounter is, oh, we know that we need more data, but how do we actually collect more data, and how do we collect enough data? So if we only use our autonomous driving cars where we install all the expensive sensors into it and use, for example, high fidelity map in the certain area, it's actually not that scalable, and we couldn't really collect enough data to be able to, fit all those data into our stack and be able to deploy that to all kinds of different ODD and geometry areas. So we are actually doing the things by leveraging the large fleet cars with low cost sensors, and then use those type of data to do the machine learning and machine training, and then deploy the model into the autonomous driving cars with high-end sensors. So essentially, there are trade-offs between the different sensor configurations. There is a perception quality versus a data quantity trade-offs here. And we know, for example, for the high fidelity LiDAR, they are expensive, but they have good range and accuracy versus other cameras. They are more affordable, but their range and accuracy is not that significant compared to the other more expensive sensors. So the key question here is, what kind of data do we need, and what will be the optimal configuration for the collection of large amount of data? So what we do there is actually we and also another thing that we know is that there is a domain adaptation problem, right? Because if we use the low-cost sensor data to generate those large amount of data and train the model like that, and then we also want to, let's see, deploy that kind of model to the autonomous driving cars where the different sensor configuration exists there. There is a essentially domain adaptation problem there. So the method that we used here is that we actually use the kind of like the low quality sensors to collect the fleet data and train the machine learning model. And then we fine tune the model by using some of the data from the sensors that used from the autonomous driving cars. So by doing that, we can fill in this domain adaptation problem. So, and we can see the performance here. So essentially, the transfer learning help us to do a good trade-off between the quantity versus accuracy. And also the domain adaptation that we just mentioned help us to unblock the power of quantity. And from this plot, the x-axis is actually the comparison between the self-driving type of sensor suite versus commodity grade, essentially low cost sensor shield. And the y-axis represents open loop planar error that corresponding to this type of like the training result from those different source of data. We can see that actually when we use 100 hours of data from the low-cost sensor suite, it can beat the performance from the 10 hours of self-driving high-cost sensor suite kind of data. And that gives us information that greater amount of lower quality data can possibly beat small amount of high quality data. So let me give a brief summary about what we have talked. So firstly, the data-driven planning system is promising. Secondly, the large-scale data set are needed to train and evaluate the stack. Thirdly, using the large-scale low-quality data from low-cost sensors can unblock large data set to train the data-driven planning system. Also, this is still an open question for the autonomous driving industry as well for the kind of like data-driven planning system. And we are looking forward to actually solve those problems together with academia and other industries companies. Thank you so much. And another additional information, we have open sourced 1,000 hours of the prediction data sets. And also there is a level 5 kit where we provide some basic tools to process those set. And there is also a tutorial where there's videos and hands-on sessions around how to use those data. So thank you. Thanks again for.
Great. Thank you so much, Jan. Let's virtually upload our speaker. That was a very interesting presentation. And with this presentation, we conclude the workshop. So I would like to open it up to all audience to ask questions to Jan, Ziran, and Yiheng on the last 3 presentations. And of course, any other questions that you might have for the first set of presentations, please feel free to unmute yourself and ask questions.
Okay, so Jan, very interesting talk. And I have one question regarding the, what is the scalability of your approach in terms of the temporary change, temporary drivable area change? For example, if you showed an example of a work zone, right, navigating a work zone with this particular work zone layout, but if next day the layout has changed, but you do not collect enough data to train the model, this approach can handle the situation?
Yeah, that's a very good question. So essentially, the model is trying to learn how to navigate around the kind of like the construction cones, not directly learn from, oh, at that particular map location, it's actually having the construction cones. So the video that we show that actually navigate around the construction cones, we actually tested by, put different type of construction cones here to see how that performs. So the key is that if we give it enough data to show it, all kinds of construction cone, all kinds of construction related area, how human driver actually handle that, then it can adapt to the new area where, for example, today's map is different from the other day's map because it's not only rely on the map, but it's actually try to learn the semantic information from that environment. So all the construction cone information is perceived by the perception stack, and then planning stack directly consider those as obstacles instead of directly read that information from the map.
Okay, all right, thank you.
Thank you, very good question.
I do have a question for you, Jan. I was wondering if you can elaborate a little bit between the computational implications of the training of the data and explain a little bit which part is become offline or which part is online versus centralized in cloud or versus on board. Can you please elaborate on this?
Yeah, sure, of course. So essentially, we train the model offline for the machine learning model, and then in the inference stage, we just directly, call that model to generate the trajectory. So that's its core idea, and of course, we also can maybe do some more fancy work. For example, applying the cloud computing information to do more, essentially to leverage more of those prompts from those methods. But the key idea is like essentially the model is trained offline, and also in the real time, we have a model portion. As we also mentioned, we also have another fallback layer which safeguards the system. So for that portion, it's actually use computational resources a lot from the real-time system.
I see. Great, thank you so much. And I also have a question for Ziran, since I didn't get the chance to ask before. Great presentation, Ziran, and great approach. This is quite, timely. I had the chance to do some work in this area, recently. I was wondering, can you elaborate a little bit on the implications between different penetrations of connected automated vehicles? I saw that in your approach, the vehicles need to connect to the cloud and do some. So what if some of the vehicles are not connected? Would the approach still be viable, or what are the implications overall?
Exactly, that's a very good question. That's exactly what we are doing right now. Where we're trying to build this so-called driver digital twin, where those vehicles that are not connected, these are human-driven vehicles. And we use kind of a hierarchical design of this system, where if, say, all those vehicles that are connected, we can receive their information. That's great. We do our cooperative motion planning and control. But what if those other drivers, they are driving their vehicles? So we will use the perception sensors on our connected automated vehicles to detect their behaviors in a short period, and then to classify those drivers into a certain type. So aggressive driver, neutral driver, or cautious driver. Just for instance, we might have maybe 10th of different classifications based on those drivers. And then we map that data to the cloud to utilize the pre-trained model. As Yiheng just mentioned, actually, the real-time inference will be pretty straightforward. We apply the pre-trained model for different drivers and then predict their behaviors. So if I say I see you, Andreas, you're driving, and you are not connected to me, I follow you for maybe 10-15 seconds based on your speed trajectories, and then map you to a certain type of driver, maybe a neutral driver. Then in the real time, we just inference the model that we train on the cloud, and then make predictions for your behaviors in the future. That's our current approach.
I see. That's very interesting. We should do some experiments in our scale city and
we actually follow a lot of your work. I think UC Riverside, they have been building some smaller size to your scale city, but definitely we look forward to learning more from you and to follow your research. Yeah.
Great.
Yeah. And I sorry.
No,
go ahead.
Go ahead, please go ahead.
It's actually divert the discussion a little bit. I do have a question for Yiheng, and very interesting talk. It's my second time listening to your talk, but it's still very interesting.
Thank you.
One question is regarding the right turn scenario that you talk about, where we don't necessarily allow the autonomous vehicles to just position in the center of the lane because it's going to be in the center of the intersection. Instead, we'll have those different blue curves to turn right, to nerf on the drivers. But which driver to nerf? How do we see, this driver is good or that driver is bad? Which is the best driver to be followed for this autonomous driving motion planning?
Yeah, that's a really, really great question. Essentially, when we try to learn from human driver, we firstly need to process the data. Essentially, we need to, check whether the trajectory from those human drivers actually follow the traffic rules. So we eliminate those data from our training data set. And on top of that, let's see if we have 2,000 drivers actually following the traffic rules in that type of turning scenarios, and then we actually aggregate them together. So we don't want to be the most aggressive one. We also don't want to be the most conservative one. So we use statistical models to actually aggregate them together to generate a trajectory where we want our ego autonomous driving car to follow. We want to keep it to be safe and also to be kind of like average performance of human driver.
Yeah, it's actually sounds like very similar to what my answer to Andreas earlier.
Yeah,
exactly. Cluster this data a little bit and then apply that in general.
Yeah, exactly.
And maybe another follow-up question to Andreas' question earlier. Yeah, you talked about the fallback, this kind of protocol where you have that learning-based model, and if that model doesn't, guarantee all the safety constraints, and you fall back to your traditional motion planner. But in this fallback transition, how do you guarantee the smooth transition? Maybe your planner has been doing great for a lot of time steps, and one time step, the result might be out of bounds. It's very, diverse. And then you fall back to your traditional motion planner, but the transition in between might be a very huge gap. And then that might introduce some maybe safety risk or some comfort, disadvantages. How do you guarantee the fallback, that protocol falls into a safe and comfort zone?
Yeah, that's a very, very good question. I will see to totally 100% ensure that smoothness is very difficult. The strategy that we use is that essentially when we try to generate the fallback trajectory, we try to get a most similar trajectory from the trajectory, machine learning trajectory. Essentially, we generate a lot of examples where, from the traditional planning stack or traditional motion planner. And then from those trajectory candidates, we identify which is safe and feasible and also most similar to the original machine learning trajectory. So in this type of strategy, we can try to, minimize the big difference or the jump between the different source of trajectory generation. But you are absolutely right. That is something that is challenging, and I think it's also a still open question. So what kind of fallback strategy should we use, and how often do we need to use it, and how do we actually ensure the fallback trajectory is very safe?
Yeah, understood. Thank you very much. Yeah,
really great question.
Great questions and great discussion. This is what this is workshop about. Any other questions from the audience for the last three speakers, or even for the speakers in the first session this morning?
Yeah, and also any open question we can also discuss here, because this is literally for the open discussion, because we have, yeah.
Absolutely. Anything that anybody can bring up for a discussion, that's very welcome. I know that it's been a little bit of a long day, and I know that some of us might be willing to, wrap this up. But this is the opportunity for anyone to ask questions or, make a comment or pose an open question for future research, anything at all.
Yeah, or sharing your research around motion planning, control, and learning for autonomous driving. Yeah,
excellent.
Feel free.
Excellent suggestion from Yang. Yes, if you guys want to introduce yourself and mention perhaps something about your research, please welcome to do so.
Yeah.
Hey Yang, I probably have a question for you. For so it's very interesting that I can see that you present if we have 100 hours of low-level sensor, we can actually beat the high-performance sensor. And I just wondering, from an industrial perspective, how many companies are going toward let's say, gathering these data from low-level sensor, like a service, let's say we run a service, and then everybody we can pay a little fee so that other people can stack a little camera on their cars, and then that gives us a low-level sensor. And I don't know if in any industry that do that, because in this area data is kind of like a very, very powerful resources.
Yeah, that's a really, really great question. To be honest, I couldn't speak for the other companies. And so the strategy that we use in the Woven Planet and we used before this lift is essentially we, as you mentioned, we install those low-cost sensors to the fleet so that we can collect that. And what I know is that even from the academia, for example, University of Michigan, together with several other research institutes, also have the initiative to collect this kind of data and also open source that data. So I think for the academia or all other industry partners, they can also leverage those sources of data. And also another source to get the data is that currently a lot of companies, including like the previous lift level 5, and also, for example, Vimo and Motional, they all share the open source data. So I think that is also another way to collect the data. Of course, it's not an ideal situation, every data is shared, but I think it still provides great opportunity for the academia and other industries to actually explore around how to use that data.
Yeah, that's great.
Thank you. And feel free to check out our data sets. We have the perception data set released in 2019 and also the planning and prediction data set released last year. And this year we also have the tutorial around how to use those data. So feel free to check it out.
Yeah, definitely. Thank you.
Thank you.
Great comment. Any other questions or comments or suggestions?
Yeah, then I have a follow-up question on this. So do you, or Lyft, do you have estimates of how much data is enough? How many hours or how many miles data is enough to deal with, for example, 99.9% of the ODDs?
That's a very good question. So my colleague from Level 5 published a paper this year around how much data is enough as a preliminary study, but the real answer for that, I think in general, I think we still don't know that. And also that's exactly one of the reasons why we always need to have the fallback layer, because we know for sure, no matter how many cars we are used to collect the data, we always might miss some of the very, very rare situation. And we want to make sure that we can still handle that kind of situation in the real time for the autonomous driving cars.
Okay.
Any other questions?
You know, Jan, in East Coast is getting a little bit late, so I guess some people might be willing to go for dinner.
Yes, yes, I
So
totally agree.
This might be a reason that we don't get a lot of, but we had a great discussion and a great talk. I think I would encourage all the audience to follow up with the speakers. You know, the contact information are available on the website of the workshop. Or they can also direct any questions that they may have to us, and then we can follow up. With this, I would like to take the opportunity to thank all our speakers again for the great talks, and also the audience for taking the time on Sunday in August to attend the workshop rather than going to the beach. That's a good sign that people like science. And then I will turn it to you, Jan, for the last word.
Oh, thank you so much for all our participants for this workshop. Special thanks to all our awesome speakers. I personally learned so much from today's talks and also the discussions. And thank you again, Andreas, for co-organizing this workshop with me. It's such a great pleasure to work together.
Absolutely. You deserve the whole credit. You did the whole hard work.
Oh, you're always so modest.
Thank you guys all. Enjoy the rest of your day.
Yeah, thank you so much, everyone. Have a nice one.
Thank you.
Thank you.
Bye.
Bye, everyone.
Bye-bye.